Okay, so welcome everyone to QTYR26. This is the first year that we are here in Valencia, in EDEM, so thank you very much, EDEM, for hosting us. The other 3 years have been in Madrid, and now we are here. I hope we have a nice workshop, that you enjoy it. First of all, as you may know, we will have 2 types of lectures, well, 3 types of lectures. One type is done by some renowned speakers, both of keynote talks and outreach talks. And then the third type is contributed talks by you. And then we will also have 2 poster sessions on Tuesday and Thursday afternoon. On Thursday afternoon, we will have as well the industry focus session that will be carried by the students of the master's degree in quantum technologies of the CSIC and several universities. The coffee breaks are sponsored basically by Valencia, by the Instituto de Física Corpuscular, Facultad de Física de la Universidad de Valencia, la Generalitat. Then the conference dinner is sponsored by the Instituto de Ciencia de la Materia Condensada, University Intragroup and Qubit team. Then we will have as a social activity a boat trip with a swimming stop that I hope we enjoy it all together, sponsored by Basque, Kilimanjaro, and Cruz and Troy. Yes, as you may know, we are there in MEDEM. The social activity will start very near from here in Boramar. You have all the specific venue in the webpage if you need it. And the conference dinner will be in Saona Casino, which is there. Also, you can find the specific direction in the webpage. And then, yeah, just if you noticed, this workshop is organized basically by PIST, an organization of young researchers in quantum technologies in Spain, which I am part of. In collaboration, obviously, with the people of the Master in Quantum Technologies and as well for local organizers. But very briefly, apart from this annual Congress, we also have some monthly online seminars organized by us as well. So if you want to apply for give an online seminar, just reach us by here or by email so that we can set a date as well. Okay? So now I will let Diego from the Master to speak to you all a little bit, and thank you very much.
Hello, everyone. Welcome to this event. As Jesus already said, this event is organized by them, by the network of young scientists here in Spain, but it's done somehow under the umbrella of our master program on quantum technologies. Let me see. Okay, this master program was an initiative by researchers from CSIC. And they managed, after a lot of work, managed to gather people from a bunch of universities here in Spain. You see this part, universities that participate officially. Those there are unofficial, but give a significant contribution. Everything is coordinated by WIMP and supported by several institutions in Spain. This is by the platform of quantum technologies in CSIC and the Spanish network on quantum technologies and Quantum Spain project. So let me give you a few facts about this, our master program. So you see here, we are three academic directors because there's a lot of students and a lot of professors. And you can imagine who give us more problems to us, to organizers. So one of them is Maria Jose Calderon. She couldn't come here, unfortunately, but she's online here, I think. So say hello online, Maria Jose. Then David Sueco, who's coming, I think, tomorrow, and myself. These are some of the characteristics of the master program. We have 60 credits. Yeah, it's planned for being completed in 1 year, but you can do it in 2 years, optionally. 2, it's fully online with some in-person activities, for instance, the lab courses, which are optional, and of course, this closing event, which is mandatory for the students. And everything is in English language. And the target mainly are physicists, I should confess, yeah, but also we have engineers, which are very welcome, and people with mathematicians, we have chemists, we have people with a broad spectrum. And we started actually in the course 2022, 2023, as it was a smaller program, I would say, but then it was expanded in 2024, 2025. So this now it's coming the third edition of this expanded version. We have all vacancies filled. We had 147 applications this year, people from 16 different nationalities, 20 women. Among the applicants, 460 places we have here. Yeah, so we are full for the next course now. And now, sadly, I have to announce that the vice director for postgraduate studies and research from WIM just passed away. Begoña Aguado was a really committed person. She really helped us to go on with this course, especially with this master program, especially this course. And we really regret that she just very recently, a few days ago, passed away. So a few words in her memory. Yeah. So that's all. Thank you.
Thank you very much. Hello, good morning, everyone. My name is Mateo Ibáñez, and I'm one of the coordinators of international relations here at EDEM Business School. And my duty today is to introduce you a little bit to this ecosystem, to this place, because you have come today to EDEM, to Business School. You know that this is a beautiful place in the waterfront of Valencia, in this beautiful city, but maybe you don't really know what you're doing here in this place and why you are here today. So my task today is to briefly introduce you a little bit to this place. And first and foremost, for us, if we want to talk about this place, about EDEM, about Marina de Empresas, we need to mention a very important person for us. Well, two important persons for us that are Juan Roch and Hortensia Herrero, which are a marriage that have established a business that is called Mercadona. If you're Spanish, for sure you know Mercadona. But at the end, Mercadona is the largest supermarket chain in Spain. It has 115,000 employees, an annual revenue of 40 billion with B euros. And at the end, well, this marriage, Juan Roch and Hortensia Herrero, they are Valencian, they are business people, and they decided to build what we call a legacy. What is a legacy? At the end, a legacy for them is a set of different initiatives, the initiatives that you can see here in the screen, with the purpose of giving back to society what they consider that they have received from the society for many years. At the end, it's not a secret that Juan Roch and his wife, Hortensia Herrero, are very wealthy. They are the third wealthiest family in Spain. So with all that wealth, with all that richness that they have accumulated through the years, they have decided to invest that wealth in the things, in the initiatives that you can see here. And what are these initiatives? Okay, so first of all, we have Marina de Empresas. Marina de Empresas is the place that we are right now. And it's not just a business school, because maybe you have heard about EDEM Business School. And yes, we are part of Marina de Empresas, and we are a university and a business school, and we teach all kind of knowledge related to business and entrepreneurship here. We have around 5,000 students a year across 40 programs, but we are not alone. We are not just an isolated business school. We are connected to Lanzadera, which is the largest accelerator of startups in Spain and one of the most important in Europe. And we are, therefore, linked to an ecosystem of startups that hosts 400 companies. So it's true that if you cross a garden that we have there, we have 2 buildings. If you cross the garden, you will find out that there are 400 real companies operating in different sectors, in different industries, that are being incubated and accelerated by our ecosystem, by Lanzadera. And then, as a third part of Marina de Empresas, we have Angels Capital. And Angels Capital is a venture capital society. Let's say it's an investment fund that invests only in the startups of Marina de Empresas that we consider investable. Okay? So Juan Roch is behind this investment fund, behind Angels Capital, and with his own money, he invests through this society in the most outstanding, let's say, startups of Lanzadera. We have accelerated in total since 2013, 1,700 startups, and through Angels Capital, we have invested in 70 startups. That is an amount of investment of 40 million euros, and so far we have recovered for 40 million as well to keep investing in more and more startups. But Marina de Empresas is not just the only one initiative that Juan Roch and Hortensia Herrero have built for this legacy. They also have built Roch Arena, which is the most important initiative of our legacy right now, I think, because it's one of the greatest venues for events and basketball games that we have in Spain right now. It's brand new. It's a brand new venue. It's here in the city of Valencia, in the south of the city. I don't know if you know Valencia, you have visited this place, but at the end, this is something huge because Juan Roch observed that every time that was happening a huge concert in Spain, let's say, it was always happening in Madrid or Barcelona. So if Bad Bunny, Ed Sheeran, Coldplay are coming to Spain, they always go to Madrid and Barcelona. And he was wondering, why not Valencia? And at the end, we were not prepared because we didn't have the proper venue to host these kind of events. So he said, okay, if nobody's building it, I'm going to do it by myself. And he built, through a 400 million euro investment from his pocket as well, a venue of 20,000 people for concerts and 16,000 people for basketball games, which is something huge for us. And he, apart from building Marina de Empresas and Roch Arena, he's also the owner of Valencia Basket Club. If you like basketball, you might know Valencia Basket Club. We are now competing against FC Barcelona for the championship title, for the ACB, which is like the Spanish NBA, the Spanish league. We are performing very well, both male and female teams. And we also have the biggest basketball academy in Europe, which is Alquería del Básquet. Alquería del Básquet has 13 courts in a super modern facility that Juan Roch has also built. And also, in the part of the sports, we have Fundación Trinidad Alfonso Foundation. Trinidad Alfonso is the name of the mother of Juan Roch, and this foundation is dedicated to sponsor elite athletes and also to organize the marathon here in Valencia, which is a huge event for the Valencians because we host every year more than 35,000 runners plus their families, so it's around 50,000 people overall coming to Valencia to run a marathon, so it's something very important. And if Juan Roch is passionate about business and sport, his wife, Hortensia Herrero, is passionate about art, and she owns the Hortensia Herrero Foundation, the foundation that carries her own name, which is dedicated towards art. And for me, this is a very beautiful mission of this foundation, because at the end, what this foundation does, apart from sponsoring artists, which is something similar to what Trinidad Alfonso Foundation does with sportists, this foundation, Hortensia Herrero Foundation, is dedicated, in my opinion, to improve our city, to make our city more beautiful. Why? Because it's fully dedicated to restore monuments, churches, art pieces of our city to make Valencia more beautiful for the locals and for the visitors. So at the end, for us, what Juan Roch and Hortensia Herrero think about the legacy is to build something with meaning to give back to others. They feel fortunate, as I said, so they want, with all these initiatives, to give back to others, for example, to us, and to promote all these things to promote art, to promote sports, to promote business and entrepreneurship across the Valencia society. So I think it's a beautiful thing, and as they say, giving is the most beautiful thing. So for us, we consider ourselves fortunate to have such a family like this, like the Rocha Herrero family, that are doing so many things in our city. So this is the family you can see here, Juan Rocha and Hortensia Herrero, and their daughters, Amparo, Juana, Hortensia. Hortensia is the president of EDEM, by the way, and Carolina. And talking about Marina de Empresas, about this place, as I said before, this is the biggest entrepreneurial ecosystem in Spain, even though EDEM Business School is not the largest business school in Spain. There are others in Madrid and Barcelona that are bigger than us. But in terms of entrepreneurship, in terms of business ecosystem, of entrepreneurial ecosystem, we consider ourselves a very unique place because so far we didn't find anybody that is doing something similar to what we are doing here, at least in Spain and in Europe, because at the end, connecting a business school with a super large accelerator of startups and an investment society, it's something that has not been done so far, but here in this place in Marina de Empresas. So I hope that you can also, during the 3 days that you are going to spend here, guys, that you can feel as well the entrepreneurial ecosystem that we have here, okay? And for us, this is our vision in Marina de Empresas. We believe that if there are some people that can satisfy the needs of any customer in the market, we will have entrepreneurs. If we will have entrepreneurs, we will have companies. If those companies are good and they grow, those companies, they will need more people. So they will hire people and they will pay the wages to the employees. So those companies will be generating employment and wealth. And then if that wealth is well managed, then we will have well-being in the society, which is something very important. So we believe, even though you are quantum scientists, most of you, we also have in this Congress the representatives of many important companies such as Indra, Kilimanjaro, IBM, and we truly believe that all the knowledge that you have can be transferred to these companies, and then those companies will be able to transfer your knowledge to the real life of people. So we are going to talk about these kind of things in the Congress, right? So we truly believe that you can contribute even though you say, okay, I'm not an entrepreneur, I'm not a person who is working in let's say in a business, in a company, but we truly believe with your knowledge, with your talent, you can also contribute to make our society better, collaborating with companies and generating employment, wealth, and well-being. So as an image is worthier than 1,000 words, as usually said, I just would like to put you 1-minute video so you can see how is daily life here in Marina de Empresas. Okay, so you can see here in this video how's the daily life. And as you can see, well, it's true that, well, our common thing, because there are many different people in these facilities. We have students, we have teachers, we have lecturers, we have entrepreneurs, we have workers, we have investors, we have business people. So at the end, well, we say that we are risk takers, and the common thing that we have, all of us, is that we are not waiting luck to come to us. It's like we try to forge our own luck, working every day and putting hard effort in everything we do, okay? So, well, as I said, the 3 initiatives of Marina de Empresas are EDEM, Lanzadera, and Angels, and, well, talking a little bit more in detail about each one of them. So, EDEM Business School is a non-profit foundation that is sponsored by more than 200 companies and a board of directors of 27 companies. And at the end, as we are a nonprofit foundation, all the profits that we get from our courses, from our training programs, we invest them to give scholarships to our students. And nowadays, we are giving away 2 million euros of scholarships every year. So 1 out of 3 of our junior students receive a scholarship. So this is something that we are very proud of. We have, as I said before, more than 5,000 students a year. And for us, the main KPI of them is this 95% of employability rate. You might know that in Spain, the employability for young people is not an easy thing. We arrived to a 42% of unemployability rate of people from 16 to 25 years old, which is a drama. Nowadays, the situation is slightly better, but not good at all. So one of our missions here at the DEM is to develop employable young people. Okay, so at the end, we are designing our programs and teaching them in a very practical way, so our students, they fit with the real needs of the company. So that's why they are very employable. And then we have Lanzadera. As I said, well, we have accelerated in 13 years 1,800 startups. If any of you guys wants to become an entrepreneur in the future, who knows? If you can also apply to Lanzadera. Lanzadera at the end is a 6-month acceleration program. It's for free for the entrepreneurs. We only asked to our entrepreneurs to have a strong commitment with the program to stay here in Valencia physically on-site. It's an on-site program, so we ask our entrepreneurs to be on-site and to do the 6-month acceleration program with a lot of effort, with a lot of passion. So at the end, if you want to become entrepreneurs in the future, I encourage you to apply for Lanzadera, because at the end, it's the best accelerator of startups in Spain. And something that is very important as well is that out of these 1,800 startups that we have accelerated, 70% of them, they are still alive, which is something not usual. Normally, the survival rate among startups is around 30%. So we are doubling, even more than doubling this rate. So 70% of them, they are still alive nowadays. So this is something very important. And at the end, well, we are very proud to say that 400 startups are co-living with us, and they are, let's say, giving us a lot of knowledge and sharing a lot with us. And you know, having 400 startups, 400 entrepreneurs with us that are also sharing and generating synergies with our students of EDEM and with the other people of our ecosystem is something that we are very proud of. And last but not least, we have Angels Capital. And as I said before as well, Angels Capital is an investment society that invests only in startups for Lanzadera, and Juan Roch is behind this society. He's a business angel. A business angel is a person who invests in startups. And, well, we have invested already 40 million euros, and we have recovered these 40 millions that are going to be used to invest in more and more and more companies. And we have a current portfolio of 70 companies invested right now. And at the end, I will finish the presentation saying that, well, Juan Roch and his wife Hortensia Herrero have dedicated 100 million euros to this ecosystem, to Marina de Empresas. So everything that you can see here, this auditorium, these facilities, these buildings, have been possible thanks to them, to these 100 million euros of investment. And at the end, if we go back to the legacy, to Roach Arena, Trinidad Alfonso Foundation, Mercadona, everything, at the end, this family has invested more than 1,000 million euros to make our society and to make our city better and better every day. And at the end, I will remind you that giving is the most important thing, and it's the most beautiful thing according to us. And being here today, a Monday of June at 8:30 a.m., you are already making an effort, you are already giving us very much, and for sure with your talent, with your knowledge, we will learn a lot and we will get inspired from you here at the Marina de Empresas as well. So thank you so much for giving us as well. And this is all by my side. Thank you so much for listening.
Okay, with that, we can start with the scientific part of the workshop. So also, I'll take the opportunity to thank you all for coming here in name of the local organizing committee. I'm Manuel Gessner from the University of Valencia. And I guess we can take it away right away. So our first speaker is Javier del Pino from the University, Polytechnical University of Madrid. Sorry, Autónoma, yeah, Universidad Autónoma de Madrid, sorry.
Thanks a lot. Can you hear me well? Yeah. So, yeah, well, this is a bit low res, but OK. Anyway, so so thank you all for joining me today. It's very nice to be surrounded by so many young people. It makes you feel a bit older, actually. Today I'm going to be speaking about a bit about topology and, well, more specifically, topological physics, which has some, well, it touches, of course, on quantum technologies, which is the topic of this workshop. And yeah, I will be talking about two separate lines of work that have been involved over the last years. There will be, because this is a very long session, there will be a break in the middle for those of you who want to, to just get some fresh air. And maybe, I don't know, like 10 minutes or so, if you want. And I will be very glad to answer your questions as they come up during the talk. I'm very happy to make this as interactive as possible. And of course, first and foremost, thank you all, the organizers, for this beautiful event. This is amazing. So, and well, I don't know if you can see this picture. It's supposed to be some optical cavity, and you see in the right a landscape. I hope by the end of the talk you will see what is the relation between the two. Now it seems a little bit far-fetched, but it will make sense at the end. So let's start. Just a very broad motivation of what type of systems I'm involved in. Of course, if you want to build any quantum device, any sort of sensor, simulator, computer, you have to deal with quantum physics, of course. And there is a set of platforms that are nowadays being explored. Probably many of you know the one at the top. It's superconducting circuits, or the use of transmon qubits coupled to microwave resonators. There is also cavities filled with cold atoms. This is a picture of a Rydberg atom ensemble in an optical lattice. And in general, all of these platforms have in common that they are driven. You need to pump some energy in. They are dissipative. They lose energy. That's unavoidable always. And the excitations in these systems are interacting. That's what you need anyway to have any sort of advantage, if you will, any sort of higher performance of a quantum device. You need interactions usually. So this looks at the macroscopic level very much like this diagram. Perhaps you have an absorption. This is an example of a so-called four-wave mixing process where you have an absorption of two photons and the emission of two photons of different frequencies. This is a sort of a scattering event. There are many, many, many examples of this. And no matter which platform are you interested in, you really need to know the physics of these platforms, understand them very well in order to make use of them. We are yet, I'd say, not at the level of really using these devices for any applications, except for very few cases. We still need to understand what happens. So, yeah, so during my talk, I will be motivated by this question. I will be introducing first a bit of background about how do I use, or why I'm interested in topology as a mathematical toolbox. Then I will present just one example of a system that I find interesting and is pretty common or has ingredients that are pretty common to everything else that I will show. And then the rest will be, there will be two parts. One about how can you engineer non-trivial band topology, or less fancily speaking, how can you engineer some form of interesting states in these systems. This will be very motivated by experiments. And the last part will be about, it's actually what gives name to the talk. It's about the topological organization of driven dissipative nonlinear systems. I didn't know a better name than topological organization. I mean, using topology as a toolbox to understand dynamics in any of these platforms, in these driven dissipative systems. So let's start with the topological toolbox. Perhaps some of you have heard about what is topology, and maybe you've seen pictures like a ball morphing into a cup and things like this. Very loosely speaking, topology it's about the unchanged properties under smooth deformations. So a giraffe is the same, it's topologically equivalent to a hippopotamus, and a ball it's topologically equivalent to something which looks like a Mac, unless you drill a hole into it, unless you have to rip up the space. And this drilling, this creation of a hole is what you will call a topological phase transition in this case, right? So topology is not just something that manifests in shapes, in this case, like in manifolds. It also imposes restrictions over functions defined over them. And very simply, you see this in the so-called Hairy-Ball theorem. So if you try to comb a sphere, it's a hairy sphere, it's really impossible to do that without creating whorls or tufts at any point. It's impossible, but if you do that with a torus, with a donut, then it's possible, because you can basically compensate in a way, has negative curvature in the middle, has positive curvature on the outside. You can compensate, you can use that to compensate, and then be able to comb it. So this also shows up in dynamical systems defined over manifolds. And dynamical systems are basically everything that we care about. If you consider now, here, I don't know if you can see, I drew, well, there are some arrows here. I wanted to show a case where just a vector flow defined over a sphere, where this vector flow is given by the set of all trajectories from initial conditions to everywhere you can go to the attractors of the system. This is a classical dynamical system. And here you see that if this is defined over a sphere, then if I change parameters, maybe this is a repelling node in this dynamical system, now becomes split into a repelling repeller, an attractor, and a saddle point. All of this must happen according to some topological rules. Just because this thing, it will be defined, let's say, on a sphere. So the phase transitions, the sharp changes, they all need to happen according to topological rules. And there is in fact a very well-known result from, I don't know, I think it's like the 19th century, by Poincaré and Hooft, which states that this number, which is called the Euler characteristic, which perhaps you recognize if you are working with topology as the integral of the Berry curvature, is related with the number of singularities in a dynamical system, the sources, the sinks, the saddles. This needs to be conserved. So whenever the number of any of those change, it has to happen, as you see, it happens always creating pairs, for instance, in a sphere. So in short, topology helps us understanding this type of what it's allowed in these systems. So the most renowned case that topology has been applied to and extremely successfully is band topology, the topology of band structures. So there you know that, what are you analyzing the topology of, in this case, is the mapping between, let's say, the Brillouin zone and the Bloch wave functions of a periodic system. So basically, you see that the Brillouin zone in a 2D lattice has the shape of the parameter space, in this case, has the shape of a torus. And if you look at how the Bloch wave function is defined over this torus, perhaps you find that you cannot continuously define what is called a gauge. You cannot continuously define the phase of the Bloch wave function over this zone, Brillouin zone. You cannot comb the Bloch wave function over this torus, in this case. And the number of, the number of whorls that you create, or vortexes, is what you call the Chern number, right? So, well, this, the interest about this is that this Chern number is related with the number of modes because of this bulk boundary correspondence. It's related with the number of modes that propagate in one direction over the edges of the system. So it has a physical consequence in this case. But I won't go there yet. What I just wanted to say is that band topology, although the most successful instance of the use of topology in physics, is not the only type of topological toolbox that there is out there. And another one, which is less known, is the topology of streamlines, which I will call flow topology. So now if you imagine a dynamical system defined over 2 coordinates, this white dot represents a source, and there the cross represents a saddle point. So, well, you can now you can imagine that there is a sense of deformation here. So if you make a coordinate change, you will see that the streamlines there, this is the streamlines of a dynamical system, they will squish, they will change. But if you look at the connectivity of the flow, so what is connected, what critical points in this flow are connected to which ones, this hasn't changed over this deformation. So there is a sense of robustness. And of course, there is a sense of a transition. What happens if I change now in such a way that the number of fixed points change, for instance? That will be a sudden change. That will be like drilling a hole in my sphere. So there is, with this, of course, it was developed by Russians 20 years ago. There is a way to find, to classify, to find a topological framework to classify all possible dynamical systems, all possible vector flows defined over, in this case, 2 dimensions on a sphere. And the invariant, which usually in topology is something like a Chern number, is a number, it's an integer. Sometimes it's not an integer, but in general, in this case, it's an integer. Instead of being a number, becomes a graph, that I will explain how to find in a second. So essentially, or later, actually, this will be the second part of the talk. But given the flow pattern, you can come up with a colored graph. You need also 3 colors, which in such a way that now if you look at 2 different graphs with different colors, now you know these dynamical systems cannot be deformed into one another smoothly. It has to go through a topological phase transition. Okay? So this is actually the other way around. First part of the talk, I will be talking about how to create these topological band structures on a specific platform, and then I will speak about this. So, yeah. So I will choose a particular system, because I hope you don't want to hear, 76 more minutes of topology. So I will be trying to make this very concrete now. So the family of systems that I focus on are related with a child on a swing. So if you focus on a child on a swing, then imagine, well, this is not usually how do you push yourself in a swing, but you can do that. If you change the height of the center of mass, you can map this problem into the problem of a pendulum that you are changing the length of. Okay? So the Hamiltonian of this system, equation of motion, if you will have now a frequency which depends, which can be changed in time. Okay? So there is a notion of a drive there. And this driving, which is called a parametric drive, because you are driving a parameter, has many uses. So if you do this, you can do this experiment now. If you hold a pendulum and change the length of it periodically at twice the resonance frequency, you can either amplify the motion of the pendulum or you can dampen it. Okay? This depends on the phase of your drive with respect to the oscillation frequency, right? So basically, it's the same as for a child in a swing. If you don't push yourself precisely when you are really at maximum speed, you will slow yourself down. So, well, this system is, of course, it appears in many platforms, or this Hamiltonian appears in many platforms, let's say. This idealization is useful. And there I added here something else, which is a quartic potential, because now you can imagine that, well, the case of a child in a swing. If you amplify the motion, then if nothing stops you, then of course you will start just you know, rolling over the whole thing, right? So if you hit an instability, so whenever the energy that you are putting in through this term overcomes the loss of the system, well, the system will not become stable, which is unphysical. And what happens in reality is that nonlinear corrections will kick in, right? Like deviations from the harmonic potential and so on. And this will be important. So again, the pendulum, now I wrote it as an equation of motion. I put damping in there. So the phase diagram for this system, in the absence of the nonlinearity, if I take the alpha out, you saw the quartic potential becomes a cubic nonlinearity. Now if you draw the phase diagram of this system as a function of detuning, so this I didn't write here, but detuning will be the parametric drive minus the half of omega 0, the natural frequency. So this is what it's in the x-axis, and in the vertical axis, it's basically I put g there, but it's basically proportional to lambda. It's g is omega 0 times lambda. If you use these parameters, the phase diagram was shown to be to have these so-called tonks, where the motion is stable if you are in the white region, and it becomes linearly unstable if you are in the gray region, right? So very clearly, if it turns out that if the omega p is close to this 2 omega 0, then unless you have any damping in the system will explode. It will become unstable. And but if you have damping, there is a finite region here, this region here, where the system can be still stable. Okay, and I will show in a second what it will do. But well, you see my reference there, right? From basically from Mathieu in the 19th century. Like Faraday also knew this before, so this is actually not new physics. Yeah, but now the point, if you zoom in this region here, you see this white region here where the system is still stable because of damping, because of the existence of damping, and the gray region where instability grows. So from the perspective of a dynamical system, if you look at this region, all of the trajectories here, they will go towards a single point attractor, towards the origin in this case. Basically, the pendulum, if you are there, it will relax, until it stops. Okay, because dissipation wins. But now if you go a little bit upwards, then of course dissipation will win. So you will go into the origin, but the distribution, let's say, of trajectories, it will be amplified on one direction. So in this case, if you now consider a system with noise, the distribution will not be that of a coherent state, will not be a blob, a circular blob, but it will be an ellipse, which is called a squeezed state. Okay? Which is basically the same. If you are familiar with quantum squeezing, this is exactly the same if you now put quantum fluctuations into the system. Okay? This is what quantum fluctuations will do. But now, very often, most analyses stop here, at least most, let's say, modern quantum analysis. People knew nonlinear dynamical systems before that, of course. And what happens in here? So in the linearly unstable region, where the energy you put in the system wins over the loss, well, in this case, there are multiple fixed points. In this case, there are 2 attractors and 1 saddle point. So the system has the option to choose where it will stabilize. So where it will settle, and this depends. Well, it cannot settle here. This is a saddle point. This is unstable, but it can settle here or here. And the choice depends on the initial conditions. Okay. If you have seen maybe any course of like nonlinear dynamics, Duffing resonators, and so on, they do this. They have multi-stability. So now, this classical system, if you quantize it, you can see, well, becoming equivalent to this Hamiltonian, right? This is now a resonator, creation operator, annihilation operator, and here you see that the nonlinearity, so the x to the cube term, the quartic potential becomes something like this. Becomes now a term which creates and destroys pairs, but conserves the energy. And the parametric drive, so the term with cosine of omega pt, if I go into a frame of reference which oscillates with omega p, this is maybe a bit of a technical point, but you can usually do this when you drive a system and want to really make the Hamiltonian time independent. If you do that, then this becomes a term that destroys pairs of excitations and creates pairs of excitations. It puts or removes pairs of photons, if you will, in this system. Okay? Photons, phonons, whatever bosonic excitation you want. Okay? And here I added this, but I didn't want to bore you with the details. So the derivation is really simple. It goes through taking the Hamiltonian there, defining some canonical operators there, and really inserting the whole thing. And you remove. In this case, there's an approximation involved. For the experts, is this rotating wave approximation where you remove everything that is time independent. Of course, there are limits to this approximation, but you end up with this Hamiltonian. And a small comment, in many of these systems, you will see in the literature that the quantization is done by counting the number of photons inside, or excitations inside the resonator. But this is a driven system. So it actually makes more sense to count the number of excitations that we put into the system, the number of pump photons, right? Which amounts to deciding if you put in these prefactors there, which governs the amplitude of the quantum fluctuations, if you put omega 0 or omega p. Okay, and this is discussed in this paper, for instance. But that's more of a technical point. Let's go now add fluctuations to this. So now if you consider the system is placed in some environment, with some thermal fluctuations, or is a closed system that is quantum, where quantum fluctuations are present. Now, what happens is that the quantum fluctuations that live in this dynamical system will settle around the points where the classical trajectories like to be, the attractors. Right? So you will have, if you now plot the probability density in phase space, you will see that there is a blob where the attractors are supposed to be, and they don't like to be in the unstable regions. Okay? Okay, this is whenever these fluctuations are not very strong. Whenever they are, whenever they become stronger, you will see effects like probability densities that cannot be called probability densities. They become negative and so on. Right? So the first part of the talk will be discussing examples of this regime, of the regime of, let's say, the linear regime, and then I will discuss the nonlinear regime, both under the framework of topology. So, yeah, so more pendula. So you can not just introduce energy or have some amplification effect by changing the length of a pendulum. You can also couple modes with different frequencies using this time dependence as well. So if you now consider two pendula that have different resonance frequencies, well, in principle, if you will use resonant coupling, that wouldn't work. Because if they have different frequencies, as soon as they are a little bit detuned, they won't exchange energy. But you can make them exchange energy if you place the spring between them in such a way that the spring constant changes in time. So this is a way to create a so-called parametric coupling. In the quantum sense, maybe you have heard the words Floquet engineering, but this is the same thing. You can create an effective interaction in the frame of reference of the frequencies of each mode, the rotating frame of reference. You can create an exchange hopping, I should say, a hopping interaction between the two modes. Okay? So you can, if you are able to change these things in your platform, in your experiment, well, this gives you a very flexible way to generate couplings. So among the many examples of systems that are out there, I will consider as a parametric nonlinear resonator this nanomechanical oscillator, which basically consists on some metallic plates which capacitance can be changed in time. So you can change the resonance frequency of the mode that lives here depicted in red, like a flexural mode that lives there, by applying voltages. Okay? This is very simple. This is a very simple device. It's very similar to the microelectromechanical devices that you have in your phone to sense accelerations. And then, actually, before that, I will consider a case where we use parametric coupling. In this case, we use a nanobeam cavity. So you can imagine it as two strings of a guitar, which are very small, much smaller than in a guitar. And then these two strings, they can confine an optical mode at terahertz frequencies. And the pressure of the light, the forces that the light pushes on these two strings, the so-called radiation pressure forces, can be used to control the motion of these strings very, very accurately. Okay? So this platform was developed and still exists in the lab of Evolt Verhagen in Amolf, Amsterdam. This one is from Alex Zeichler group at ETH. So let's go to the first part, where I discuss some physics, some actual results. So in this first part, I will talk to you about how can you engineer in these strings of a guitar optomechanical system, how we can engineer interesting topological states. In this case, there will be, I'm interested in engineering one-way or non-reciprocal states. Non-reciprocity means that if you have some medium that can support some propagating waves, then if you change a source and observer, the result doesn't, well, it does change. So in this room now, if you are hearing me making a noise, then this means that I can hear you back, because the propagation of acoustic waves is reciprocal in general. So in order to engineer non-reciprocal propagation, we really need to do something to this medium here. In particular, we need to break symmetries. Okay? So this was done in collaboration with experimentalists from Amolf, led by Ewout Verhagen. Jess Slim was the PhD student back then who did most of the experiments. And part of the results that I will present have been done also in collaboration with theorists, Andreas Nunenkamp, Clara, and Matteo, all now in different places where they used to be. But I would like to appreciate them all. And now, the logic of this is that, well, if we think of a condensed matter system, a lattice system or a crystal, then, well, due to, let's say, Coulomb interactions, then we have some structure, and that's it. Maybe we can fabricate a different one, but we don't have that much of tunability. Now, if we instead consider resonators, photonic resonators or mechanical resonators that are coupled, we can engineer the dispersion of the waves propagated in this system, so create the so-called a metamaterial, just by playing with the couplings and the connectivity and so on. And one may think that this is enough to now mimic everything in condensed matter physics. And of course, this is not the case. And it was realized very soonly, back in the 70s, that there are properties that are not necessarily related with the geometry of the waves or the dispersion, just the dispersion itself, but with something more profound, namely topology. And an example of this is if you consider a 2D electron gas, where you pierce, this is a system which is conducting. If you pierce it with a magnetic field, you will create some orbits, some cyclotron orbits on the inside, Landau levels are called. But on the edges of the system, these orbits will be skipping. So the system will be conducting currents over the edges, even though it becomes insulating in the bulk, right? And it was realized by Taules, basically, that the existence of this, the appearance of these edge modes, is related with a topological invariant, the Chern number that I mentioned before. So whether these Bloch wave functions on this system look like a cup of coffee or pants, okay? Very superficially. So now, in this case, what was done was breaking time reversal symmetry. This is what a magnetic field does. But how do you break time reversal symmetry in an artificial system like a photonic system or a mechanical system where you have no charge? How can you use now a magnetic field for that? And it turns out that you cannot do it in the same way, but you can still use this parametric coupling idea that I mentioned before to couple things with different frequencies to do that, as I will show. And again, the idea is the same as before. We are able to, if you are able to modulate the coupling between two modes, but now having imparting a phase there, you will be able to now create a Hamiltonian, which is the same as before. It's a hopping Hamiltonian, but now imparts a phase there. And this phase, it's very important because this is the same phase that it's the so-called Aharonov-Bohm phase, is the same phase that an electron, which is circulating around the region where there is a magnetic field present, feels. And it's related, the overall phase that an electron accumulates over a loop around a region where there is no magnetic field, but there is a vector field, a vector potential present. It's proportional to the flux that goes through here, right? So this same phase you can now engineer for any system, not necessarily an electronic system, just by playing with parametric coupling. And this idea has been used in all of these papers are from different platforms, in photonic systems, in vibrational systems, and so on. We did it in this optomechanical device for vibrations. So how we did it. Now, I just very briefly explain what an optomechanical cavity is, but physically you can imagine it as a system where the resonance frequency, a cavity where its resonance frequency changes depending on a mechanical mode. So you can imagine it as Fabry-Perot cavity. It supports an optical mode, and now a mirror is allowed to move. So as the mirror moves, it changes the optical resonance frequency. So if you place the drive somewhere else, a laser, then because the resonance frequency is changing with the mechanical motion, you will have like a response of the cavity which moves past the frequency where your driving is or not. So you will be able to change the number of photons inside the cavity by applying some motion in this mechanical state in this movie mirror, and also vice versa. So if you now place a lot of photons inside the cavity, you will be able to create a motion in this mirror, just because this is exerting, the photons that we put in the cavity are exerting forces on the mirrors. So again, I put here the system where we did this. There are many examples. This can be done in various other platforms. Again, superconducting circuits, collatoms, you name it. But we did it in this case. And another interesting point comes when you have mirrors. In this case, are the strings with different frequencies. You can now, you can now create forces. Now the spring that connects them, schematically, is the optical field inside this cavity. So if you are able to change, if you are able to create a force or a coupling between them, which oscillates at a frequency, at the right frequency, you will be able to couple the modes even if they are at different frequencies. And as I explained before, you will also be able to impart phases there. So you will be able to mimic what the Aharonov-Bohm effect does, but now for the mechanical vibrations in this system, this mirror moving or this mirror moving. So we have to now actuate on the cavity to do that. And in this case, you have many mechanical modes. These are the fundamental excitations and so on of these mirrors. They all live at megahertz frequencies and so on. And now this is an experimental result. Now let's consider that I take three modes inside my cavity, three mechanical modes that live there. I couple them by changing. I have to apply lasers in such a way they change the amplitude of the radiation pressure inside the cavity. So they have to apply forces at the frequency difference between these three modes. So I need three lasers. And if I do that with a phase imprint, then I can now record how the mechanical motion is going to be in this system. And now look at the top panel there. Here I'm exciting the mode 1 there. I have no phase in there. I'm just exciting the mode 1, and then I switch off the drive, and I switch on the couplings at about time 0. And then you see that the excitation shares into mode 2 and mode 3 with different heights, but evenly, right? They excite at the same time, right? They go at the same time. But if I now put a phase in this effective coupling, then I can make the excitation go chiral. So it goes 1, 2, 3. If you see the order of the maxima, it's now it's now 1, 2, 3, 1, 2, 3. The excitation goes in a loop. Okay, this is the same physics that have been observed in other systems like superconducting qubits. I mean, you can even do this with pendula, if you will, if you are able to control all of this. So now, if you scale this up, this is a very small lattice, so to say, it's just 3 modes. But if you are able to scale this up into a larger array, then you can use this idea to create modes, propagating waves over the edges of the system that only go in one direction, that break the symmetry, or chiral modes, which have, as I mentioned before, they have to do with the existence of a topological invariant of the wave functions that will live in the block. But anyway, this has been done in many systems, also in these gyroscopes, which are like a millimeter scale. It's really agnostic of the platform. It's just waves, propagation of waves, linear propagation of waves. And you can also now put your platform to the test and try to grow the number of modes that you have in such a way that you create a lattice, in such a way that you start observing these chiral edge modes, these one-way states, just because you are adding more and more lattice sites. In this platform, you cannot add more than 5 or 6, but it's already enough to observe some of these effects. But all of these physics are related with they don't relate with interactions between the particles in your system. So the phonons, these vibrations themselves, you could put there 1 vibration, or you could put 1,000,000 of them, and they will not know the difference because they don't have any attractive or repulsive interactions between them. It's just classical. They behave as classical waves, or the same way as electrons, if you will just have 1 electron in your system, right? Single particle excitation. So we haven't used any of the fact that these excitations are bosons, for instance. So how can we do that? The easy way is by putting squeezing, the so-called squeezing interaction. Again, now instead of modulating at the frequency difference, now we actuate with forces, radiation pressure forces at some frequencies, and now we can have interactions. You see them there. They are similar to the ones that we created with the parametric tribes, where we create pairs of excitations in different sites. So this doesn't conserve the number of excitations. Okay, this is the same interaction that you have in a nonlinear crystal that is used for parametric down conversion if you are working on that. And this will indeed is called squeezing because it will squeeze the phase space distribution in one direction. So it will attenuate the motion in one direction and grow in another direction in phase space. So depending on the phase that you are using. So now, so formally, once you have squeezing and look into the dynamics of these modes, the dynamical metrics that governs this, like the Heisenberg equation of motion, it's non-Hermitian for bosons. This means that now the eigenvalues of this guy, which tells me whether my excitations are gonna, how they are gonna behave, whether they are gonna be oscillatory, decaying, amplifying, they are gonna be complex, which is a very different scenario for fermions. And this means that you can have amplification indeed. So the complexity means that you can have damping instilled by this two-mode squeezing or single-mode squeezing, and also gain. So an example of this, as an example of this, we consider 2 modes. These are 2 mechanical modes on the same structure again, where we are driving them with twice the resonance frequency. And we are also coupling them. and we have a phase that we can control in the middle. So the physics of this is equivalent to the Aharonov-Bohm effect. Now you can see this by noticing that the squeezing, so the creation of pairs of excitation, is equivalent to the creation of an excitation and the destruction of an anti-excitation. So in other words, like A squared is the same as A times A dagger, right? Which is trivial, but it allows you to recognize the fact that the system accumulates now. It forms now a plaquette in this creation and annihilation space that can thread a flux there. So you can then use these phases to control physical properties. In this case, in short, we use it to control the amount of squeezing. So you can, just by changing the phase, you can go from a non-squeezing to a largely squeezing state, and this depends on basically how do you mix the hybrid modes, okay? So if you are interested in this, I can tell you more. But you can also use this type of coupling and squeezing. You can play with both of them at the same time to create one-way or chiral edge modes. So modes that, again, propagate on one direction. Now with the addition that because you have complex eigenvalues, because you can have gain in your system, you can also amplify. You can have chiral amplification. So what this means now, if you consider 3 modes, with these 2 mode squeezing interaction and hopping interaction, the diagram, forget about this picture, the diagram in particle Hall space will look like this. Well, now if I'm now considering an experiment where this is an actual experimental results, where I'm driving this mode and observing what comes out here as a function of the phase that it encloses, and also the other way around. And now driving here and observing what comes out here. Okay? So now you see this is now the amplitude. In this case, this is the amplitude of the mode 2, as you are driving the first one, versus time and versus this flux. And you see that basically the excitation grows from mode 1 into mode 2. So you see a redder color when the flux is equal to pi/2, but it actually becomes attenuated with the opposite flux. And for these same parameters, if I had driven mode 2 instead of the 1, I will not see anything coming out on mode 1. So the system amplifies from here for a given setting of flux, let's say flux equal to pi/2, it amplifies energy from here to here, but it attenuates it in the other way around. Okay? And this was, by the way, this idea was also shown in photonic systems, and now people are trying to understand whether this is useful also for, well, of course, for sensing, for amplifying small signals with a small added noise. But let me show you. I'll maybe stop in 3 minutes or so. Just wanted to show you another example of what can you do when you have hopping and squeezing interactions all together. And something else that you can do is to create what is called a bosonic key-type chain. If some of you are working with Majorana fermions, maybe you know very well the key-type chain, the fermionic one. It supports this. It's basically a chain of modes that have hopping and interactions and pairing. And if you look into the bosonic version of that model, it will not support Majorana fermions. It will not have these ampere excitations at the edges that are so elusive. But it will have some interesting properties. So it happens that if you now look at decompose the modes into quadratures, into x and y quadratures, namely, the part of the excitation that goes with the cosine and the part that goes with the sine, then you see that they can decouple. So the equations of motion are such that when the hopping and the squeezing, the 2-mode squeezing are equal, they can decouple in one direction. And you can show that this leads also to non-reciprocity, to one-way behavior that now doesn't show up in the energy. It shows up in a phase-dependent way in other observables. You can now, for instance, see that you drive one of the quadratures. So you drive a wave with a cosine, let's say, proportional to a cosine of time. And then you see that, that in this case, let's see which one I'm talking about. Yeah, so you see that nothing comes out over P1, for instance. But if I try now, what is it? Let's see. Well, you see that this is asymmetric, right? So you see that basically in this region, like if I drive X2, I see excitations coming out on X1, but not the other way around. If I drive in X1, nothing comes out of X2. Okay? It's a weirder type of non-reciprocity. And this can be used. We prove in another paper that this can be, well, I should mention that the original idea for this quadrature non-reciprocity comes from a paper from Ashclerk and McDonald from 2018. But we tested this idea and showed that indeed this quadrature non-reciprocity has to do with the topological phase transition. It's actually the amplification that you obtain is related with what is called the closure of a point gap, which can be ascribed a topological invariant. If you are more interested about this, I can give you more details. And this can be used for enhancing the responsivity of the system, and perhaps for sensing applications, it's not so clear that you can use any of these systems to enhance the signal-to-noise ratio, but you can enhance the signals. And yeah, and this is basically the test of that. This is a system where you are driving an X quadrature, you have a bit of detuning in one mode, and then it comes back as a P quadrature. So in short, you can make the system amplified waves that go in one direction without any backscattering, and then amplify in the opposite direction without any backscattering to the other side. Very loosely speaking. So then this is then where I start with the second part. Yeah. So maybe now we can take a break if you want, and then I continue. Just to overview what I will be talking about. So far, yeah, this picture is not showing up for some reason. So far, I only spoke about the phase diagram region where I can have squeezing, but the system only has one stable state. It's monostable. Now, if I keep driving it, it will eventually bifurcate. It will create new solutions. And you can see that this is the analog of a phase transition in an open system. So from one attractor, you will go into many attractors. If you have also noise, quantum, or classical noise, the distributions will now spread over these multiple attractors. So this is what I will be talking about, this second method. And yeah, maybe I can do that in a second. Yeah. Yeah, if there are some questions now
for this part
about this first part.
Okay, maybe we keep the questions for at the very end. And if there are no urgent questions at this point, how long do you want to break?
So I think maybe 5 minutes.
Yeah. So the coffee break will be later. Is not yet ready outside, so it would just be to take a breath and digest the things that we've seen so far. So we reconvene at 10, 5 minutes?
Yes.
Okay.
Yes. Perfect. Una parte. Vale, perfecto.
Genial.
So, yeah.
Okay, let's try to find our seats so we can continue on time and finish also on time for the coffee break, which will be at the end of this talk, so at 10:30. Please take it away for the second part.
Thanks a lot. So now in the second part, I'm gonna switch gears a little bit, still speaking about examples of driven dissipative nonlinear systems, and now using topology for a different purpose. Instead of trying to mimic a topological system, instead of doing that, now I will be analyzing a system, a given system, using topological tools. So like a bit like inverting the whole thing. So this research has been done well during mainly during my time as an interim professor in Constance, and also started before as a postdoc at ETH. So I'd like to appreciate Odette Silverberg, Alexander Eichler, Gianluca Rostelli. And now we are working on the continuation of this together with my PhD student Alejandro at IFIMAC in Madrid. So now I'm going to give you a different notion of what it's a topological phase transition changing it with by a topographic phase transition. So now imagine that you have some landscape on the surface of Earth with some towns, E and B, that are connected through rivers, but maybe we don't have anything connecting it to other points. So there are maybe towns that are isolated, like, well, I didn't draw them, but maybe there are others. And now imagine that you wait for millions of years, such that the topography, the landscape, how the hills and the valleys in this landscape have changed. And this means also that now water it's able to flow in this changed landscape, and perhaps now connecting places where that were isolated. So the connectivity of this landscape changes. In this case, the connectivity through rivers and watersheds and so on, by changes in the topography. So now this can be translated into a dynamical system. Now, if you have some potential, let's say, on a surface, now changes of this type will make some of the fixed points of this dynamical system be connected or disconnected through these changes. So this can be formalized in a very elegant way, and the idea is that now if I have a flow this is now the set. Again, I say this is the set of all of the trajectories from initial conditions into the long time behavior. So these black dots are the attractors, and the crosses are the saddles, and so on. So now you can now split the phase space in order to come up with an invariant. You can split now the phase space into regions which have the same behavior, with same topological behavior, actually. So if you see, in this region, all of the trajectories that start from somewhere, they all end up in the left attractor. All of these ones, they end up in the right attractor. And in the middle, you see that I isolated trajectories that go from this source, from this repeller, into this attractor in the right. So by doing these cells, we can now split the phase space. This is the so-called Morse-Mail complex in mathematics, and from that one can come up with a graph, which is sort of like the dual of it, that is unique for this flow. And an important point is that if I now do a small deformations over this flow, if I change coordinates, if I change parameters, not in a very dramatic way, the graph will stay the same. The flow may change, but the graph will stay the same. And the graph can only change whenever there is a phase transition, when there is a big change. The connectivity has changed, for instance, right? So I don't know why this has this low resolution, but basically the system that I have here, it's sort of a cavity that I'm driving it with a 2-photon drive like this one. So this is proportional to this. It's also lossy, of course, and I'm also considering a drive like this one, which it's let's say it's proportional to 8 integer. Okay. So yeah, so this is a system actually modeled that it's a nice model for this microelectromechanical system, and without going too much in the details of what are the different phases that you observe in this diagram now. Here we are changing the frequency of an external this 2-photon drive and the frequency. Well, no, in this case is the amplitude of this force. You can see regions where there are different numbers of attractors. So in this region there is only 1 attractor. In this blue region there is 5 attractors. In the pink you have 3 attractors. So that correspond in this case to 2 So actually, it's not 5 attractors. In this case, is 3 attractors and 2 unstable states. In this case, it's 2 attractors and 1 stable state. You can measure this phase diagram in the lab, characterize it. And the point is now that that if you look in this pink region here, you can recognize regions where there are 2 attractors with 1 saddle in the middle at both sides. So you see like they form sort of they merge at a point, but then this pink region continues upwards. What is the difference between this is that, well, in both cases you have these 2 attractors with 1 saddle, but if you look at the winding, so at what the flow does around these attractors, in the second case, when you go upwards, it goes in an opposite chirality. So in this case, it's going clockwise, and then it's going counterclockwise around the other attractor. So what this means, and you can, by the way, calculate or draw the graph invariant and see that they are different. The topological phase transition in this case is basically that the system goes from having a particle-like spectrum to a hole-like spectrum. The effective potential, if you do the math, it goes basically from a ball to a hill, right? And this you see as a change of a chirality. Or if you look at the linear response of the system, you will see that in this case you will have sideband peaks around a frequency that are red detuned. They have less frequency than the frequency of the parametric drive, and in this case, they are blue detuned for the experts. Okay. And the colors are not showing here, but you can see fancier phase transitions. If you go along this region with 3 stable attractors, you can see cases where the connectivity changes without anything else changing. So if you see here, the attractor with the red trajectories around, the red trajectories, they can go through the saddle, through saddle 1. They do not touch the saddle 2. And if I go from here to here in parameter space, then they start connecting the two saddles. So in this case, you will see that in the time evolution, well, you will see that it's not starting from one attractor and driving the system away. The system will have, for instance, if you drive it there, it will have a hard time reaching this attractor because it's not connected to it. It will only go through the other saddle to this attractor, whereas in this case, it will go right away. And the noise, classical quantum noise, they will also inherit this. Okay? I will show cases that are a little bit more striking where this happens. And this is just classics, but this shows up also in or manifests in the quantum dynamics. So now if you plot for instance, now it's the same system now. It's a system where I have a force that is resonant and a 2-photon drive. This system has been demonstrated in 2020 or so to host Schrödinger cat states in the ground state. So basically, what is in a Schrödinger cat state? It's a superposition of 2 macroscopic phase states, so 2 macroscopic coherent states. Basically, it's basically the coherent state alpha superimposed by the coherent state minus alpha, and this means that basically classically you have 2 attractors, one at alpha and one at minus alpha, and the quantum fluctuations fill them. So if you now look at how these attractors and flows change the states, you can take a cut on parameter space. This is a cut on the parametric drive frequency, and it's not important what this plot does, but you see that the attractors, the arrangement of the attractors, these are saddles and these are attractors, they change. So the number of them changes, and you see the probability distributions also changes about them. Okay, so this is all manifesting. And how can you measure something a little bit more unconventional. Well, now you can see also these changes of particle-like with Hall-like spectra. So the chirality around the attractors will also impact observables. In this case, it will impact the linear response function. If you want to know more details, I'll be happy to tell you. But I will happier to tell you something else. That is that, well, first, if you, of course, the system, the quantum system behaves very much like a classical system whenever the interactions are not very large. So in other words, in these nonlinear devices, if you place a photon and then you need to place millions or billions of photons in order to see an effect, that system is not going to behave very quantum mechanically because it's not sensitive to few excitations populating the system. But there are cases like in these devices here, which by the way I didn't say they can build out of a microwave cavity coupled to a transmon qubit, where if you place a photon in the system, it shifts the resonance frequency of the cavity so much that now if you place another one, it's not able to interact with the system because the resonance frequency is away. This is the blockade regime, where then the photons then start behaving more like fermions, if you will. And in these limits, you can then imagine trying to come up with any sort of a topological framework, a topological invariant. Well, it's not so easy because now the flows, the phase space flows, are not really telling you what the real dynamics of the system are. So they do not, are not so efficient as in scaffolding. But again, now if you use other tools, like you can, for instance, look into the generator of the open system dynamics, the Liouvillean. If you diagonalize it and look at these particle Hall flips, these chirality changes, you will also see them. But it's a mess. It's work in progress. It becomes much harder to interpret now in this case. But in principle, the message here is that this topological toolbox for classical systems has some degree of applicability into the strong quantum regime. So now let me show you some last results on a more exotic type of long-time dynamics, which is limit cycles. And maybe you know there is a very simple oscillator model, which is called the Van der Pol oscillator, that is such that basically the system will be unstable. You have a gain term. You see this minus mu x dot. That's an anti-damping term, which pushes the system outwards in phase space. It makes the system unstable, but then this is compensated by a nonlinear loss in such a way that when you go very far from the origin, the nonlinear loss starts becoming larger and the system stabilizes into an orbit. These limit cycles, this is the simplest case, but they show up in basically every nonlinear system with enough complexity. It shows up in lasers, it shows up in ecological systems, in really many scenarios across physics. And it turns out that these limit cycles basically mean that if you start, in this case, if you start from every point in phase space, you will fall into this orbit. But they can sometimes coexist with other fixed points. So they can be very complicated phases, actually, there, where the limit cycles are present, the attractors, the saddles, everything. So the question is, can topology tells us something about what limit cycles, where attractors are allowed to be? And it turns out that it can. And I won't show you the construction of the invariants now, but you can find an invariant that does the job. Is the analog of these graphs. Now they are a little bit more complicated. In short, what this invariance tells you is how phase space is connected, whether basically you take a flow with perhaps limit cycles and attractors and saddles and so on, and then you cut pieces of it. And then you take these pieces out, you call them atoms, and then you see how these atoms are connected together. With that, you can construct an invariant. And if you apply this to a very simple model, which is, again, is a cavity, we put also nonlinear laws besides of linear laws, and you can have very complicated phase diagrams as a function of the nonlinearity and as a function of the parametric drive. We can even ascribe names to everything that we see. Of course, this becomes very messy. Like you have, like the alpha 2 bar O, alpha 1 bar phase. But it doesn't matter so much. The point is now that phase transitions can occur that involve now the creation, not just the destruction, the annihilation of fixed points, but also of limit cycles. So here, for instance, you see this source becomes an unstable limit cycle. This unstable limit cycle then is such that trajectories, this is repelling, meaning that trajectories, including quantum fluctuations, will not be able to enter there. It creates a barrier, and so on. Limit cycles can merge. So many things can happen. And this impacts the quantum dynamics of the system. So now if you plot the evolution of the Wigner function, the probability distribution in phase space, you always start from the middle. You see that depending on which phase you are, the dynamics will be different. So in the simplest case, there is just one limit cycle. The wave packet, let's say in phase space, expands, and then it falls into the limit cycle. Nothing so fancy it's happening. But there are more complicated cases, for instance, where these barriers exist, these unstable limit cycles, where the system cannot cross them, and it becomes, it has, different dynamics. You will be able to observe these differences in an experiment. You will be able to characterize these different topological phases just by tracking how the dynamics work. Okay. So now that we know, in principle, that we could do this in a single resonator, in this case, just a single mode. Now, we would like to really go back to larger systems, such as those studied in band topology. So band topology is about lattices, right? Now, usually, what will happen is that if we have a nonlinear array of resonators, we cannot apply band topology right away, because effectively we cannot define block wave functions. If we have a nonlinear system, we cannot use the superposition principle. Things become very complex. Now, how do we go from one to many? This is a bit more of ongoing research. For one, we know that by now that we could have a flow in phase space, and we can ascribe a graph invariant to that. Now, when we have many, the phase space now it's sort of a blurb like this in high dimensions. It's twice the number of modes, but still. If we are a little bit clever about how we play with interactions, we can now find that there are spaces that are where the dynamics are perhaps slow, and spaces where the dynamics or dynamics between spaces that will be fast. So this is something that we are now looking into, and it relates to the topic of metastable dynamics and the so-called avalanches, which are also well studied in nonlinear networks like neural models and also ecology and so on, but not much on this context towards quantum technologies and so on. Now, technical difficulties that arise whenever you try to solve the dynamics of a nonlinear system comprising many modes, is that the number of stationary states, the number of fixed points, scales exponentially. So just to show you an example, these are the stable fixed points as a function of frequency. These are the amplitudes of them. For 2 oscillators, you see many curves. Look how many you see for 3 oscillators. And the phase transitions, the bifurcations, they become more and more complex. So it's not just that the number of fixed points changes, but also the connectivity between the different parts of phase space can become more and more complex, and eventually the system can become chaotic. There are regions where the systems will always be chaotic when it's sufficiently high dimensional. So we develop a toolbox to basically to calculate the fixed points in a very efficient way, and with the assurance that you will find all of the fixed points, which is usually not the case. Like if you will try to now do time evolution to find all of these fixed points, you will need to sample huge regions of phase space. You will need to start from every point in phase space and see where you fall, right? So that will be horrible. In this case, if we don't do it like this, or if you're interested, I can help you out. And with that, I'm really at the end of my presentation. So the bottom line is that topology, it offers us a toolbox to extract information, global information about dynamics. It has been very successful in lattices structures. We can try to engineer this type of topological lattices in devices that have nothing to do with condensed matter, like, for instance, these vibrational modes. And also, now we can use topology to explore nonlinear dynamics, which you always have to do if you have an interacting quantum system. So far, mostly I showed classical nonlinear dynamics, but many of the things that you see are translatable into the quantum regime. And actually, you cannot understand quantum mechanics if you don't understand what is the classical background behind it, right? How can you distinguish? How can you know that your effects are truly quantum if you don't know what is the classical dynamics behind that? And I show you some examples in different cases, fixed points, limit cycles, and so on. The outlook will be to really grow up this up in dimensions and to use this notion, this knowledge of topology for something useful. So perhaps to develop new quantum control protocols, maybe, where you know that the system is extremely responsive when it's close to a phase transition, at least in the classical limit. So maybe you can use this for either to sense a perturbation in a nice way, or to switch states very fast. But this is a bit speculative. And if you are interested, there's a bunch of stuff, there's a bunch of references that we worked on, and yeah, I'm very happy to take your questions now if you have them. Thank you.
Yeah, thank you, Javier, for a very nice talk and for staying on time. Also, we have 5 minutes for questions before the coffee break, so please. There's one here, so I understand this is the mic.
Hello. Okay, so I have a doubt about the last slide before the outlook.
Yeah.
Where you show that one.
Yeah.
The bottom, the Wigner functions.
Yeah.
Are they like for a real state for a cavity?
Do you mean if they are experimental or?
No, like if you have, like, let the cavity evolve until it reaches that state.
Yeah.
And they are all classical because they are no. Okay.
And in the long term, they are always classical. In the transient evolution, you see, well, it's tiny, but you see some. Okay. They can be negative in the transient, but usually, quantum dynamics are usually related more with transients at steady states. Here, because of loss, basically everything, you always end up with a classical mixture, but. But it will be interesting to see if you can also see this type of. You can use topology also to understand regimes where you have truly genuine quantum. Yes.
Okay, and you also mentioned cat states, so the bottom right one could be
That's a cat state.
Okay, but there are no fringes there, right?
Yeah,
so
it's a classical cat state.
Okay.
Yeah, of course. Yeah, so I think is that in this regime that we looked at, also that's also the balance between quantum fluctuations. The size of the quantum fluctuations, you could say, is fixed because it's what you have in the vacuum. But then the distance between the attractors will tell you how likely is that these quantum fluctuations switch you between attractors. And in the cat state, what you have is that you have a strong switching of quantum fluctuations between attractors, but you can also have superpositions, quantum superpositions, because of tunneling events. So in this case, the tunneling events are so little that is basically they are below this noise. But the cat state, the one that you are talking about, will be basically this, in a regime where the quantum tunneling is dominant.
Okay, thank you.
Thanks.
More questions? Yes, there's one here.
Thank you. Thank you very much for the lecture. So in the first part of your talk, you defined this synthetic Aronoff bomb phase to create this chiral dynamics. So this recalls me at least the persistent currents in conducting rings. So, but that's a spectral property. And that means that's only a property of the ground state. The first excited state would circulate in the other direction.
Yes.
So, but viewpoint is different from the point of view of a dynamical system. So, can you connect these two ideas?
Yeah, so the persistent currents, yeah, exactly. So I think maybe you are even referring to, there is, let's go there. This one. Yeah. So actually, this Nature Physics paper is the one about the persistent currents. So the ones in the ground state, the chiral ground state currents. Yeah, and that's true. So if you have a single excitation in that case, you have just a chiral excitation moving, and in that paper they show that if you have more than one excitation because of strong interactions, then you have a hole which is moving in the backwards direction. So we cannot have that second dynamics because the interactions here are really, really, really tiny. There are platforms where you could have that, and actually we are sort of working on that, where you can have phonons do this, especially when you are strongly coupling them to transmon qubits, so they inherit the nonlinearity. So you could do that. Whether this is a persistent current, so it's complicated. So so it turns out that that really depends on your measurement of persistent current. So you can measure a current of bosons that is going there, and that will be definitely there. Whether that can counter, for instance, if you have non-equilibrium bats like we have here, bats at different temperature, that's another question. So whether this persistent current can be measured, that's not a trivial question, but it's there. Yes. Yes.
If there's one more quick question, we can still put it before the break. If not, we can also, Javier will be around until Thursday morning, so you can ask him on the boat if you have more questions that you're not able to ask now. So then let's thank Javier again for this very nice lecture. And we now have the coffee break prepared outside. I still would like to ask those that give a talk in the session after the coffee break to please gather here and have a quick chat with David about the technical details for how this is going to work. And enjoy the coffee. See you.
Welcome, everyone. So now we are going to start with the contributed talks in the Quantum Technologies for Young Researchers workshop. Thank you, everyone, for being here right now. And the first speaker is going to be Hilario Espinosa Martínez from Universidad Carlos III de Madrid with his talk, Microwave Free Vector Magnetometry and Crystal Orientation with Nitrogen Vacancy Centers using Bayesian Interference. So, thank you, Hilario.
Thank you for the kind introduction, and good morning, everyone. Well, in this talk, I wanted to present one of the latest works in my group, in which I will show some unconventional way of doing magnetometry with nitrogen vacancy centers. Normally, some standard techniques use microwaves or require precise alignment of the crystal, and this method leaves these two requirements. So for those of you who might not be familiar, the nitrogen vacancy center is a point defect in the diamond lattice consisting of a substitutional nitrogen atom. I don't have the laser, I think. Oh, well, it's very weak. Don't worry. Adjacent to a carbon vacancy. And these defects host an electronic spin with some remarkable properties. So for instance, it can be optically initialized and read out. It maintains long coherence times even at room temperature. Also, its spin levels are sensitive to multiple perturbations, such as electric fields, magnetic fields, temperature, or pressure. So it is an excellent quantum sensor. Diamond is biocompatible, which enables some applications in biological environments. And since it is an atom-like defect, it has access to a very small sensing volume, and therefore it achieves very high spatial resolution. Some of these properties come from the electronic structure of the NV center. The NV has a triplet ground state with total spin S equal to 1. And this ground state is usually where most of the control using microwaves happens in most standard techniques. Then when the NV is illuminated with a green laser, it gets excited to another triplet state, from which it can decay back, emitting one photon. Or if the NV was in the ±1 manifold, it can also decay through a metastable state without emitting photons. In fact, this decay path, as I said, is non-radiative, and also it relaxes preferentially to the zero state. So this mechanism is precisely what enables both spin state preparation, initialization of the state, and also readout through the fluorescence of the red photons. Then the magnetic sensitivity comes from the Zeeman effect. The NV energy levels are shifted with the projection of a magnetic field onto the NV crystallographic axis. Since in the diamond lattice, the NV can appear in 4 different orientations, given the lattice structure of the diamond, by sweeping a microwave field over an ensemble of NV centers, one sees a series of dips in the photoluminescence corresponding to these 2 transitions for each of the 4 NV or 4 differently oriented NVs. So by assigning each dip to one orientation, one has enough information to reconstruct the vector magnetic field. This is the most standard technique. This is called optically detected magnetic resonance, or ODMR for short. However, microwaves are not always the most practical in certain environments, such as metallic or biological samples. So instead, in this work, instead of using microwaves, I wanted to exploit cross-relaxation. In an ensemble of NVs, some of them might depolarize really fast. These NVs that depolarize really fast are called fluctuators and do not contribute to the optical signal. This might have short coherence because of strain, or maybe they are closer to the diamond surface, for instance. If other NVs are in resonance with this fluctuator, they can exchange excitations, and therefore they can relax through the fluctuator, reducing the overall photoluminescence. This is cross-relaxation. This happens naturally at zero magnetic field for 2 NVs that are differently oriented. But if I include some magnetic field transverse to the sample, these dips in photoluminescence will happen at specific values of the magnetic field that I'm sweeping in this case, vertical direction. This is for 2 orientations. If I include the 4 orientations, I will have some spectra, some photoluminescence spectra, like this one, from which I want to extract the magnetic field information. One realization that we had is that in order to calculate or to compute the positions at which these photoluminescence dips happen, we don't need to do any Hamiltonian diagonalization. We don't need to really compute the NV energy levels. We just need to know if the total magnetic field has the same projection over 2 differently oriented NV centers. Or, geometrically speaking, it is equivalent to say determining if the total magnetic field lies within one of these 9 symmetry planes. So in order to build a magnetic field sensor with this principle, our idea was, let's say that initially I have some magnetic field that it is unknown to me, but also I don't know what the orientation of my diamond crystal is. What I can do is to rotate the sample and also apply additional magnetic fields so that the total magnetic field crosses the 9 symmetry planes. Every time it crosses one symmetry plane, I will have a drop in photoluminescence, and from that, I can invert my signal in order to infer the parameters that I want to know. In this case, again, the orientation of my crystal and also the magnetic field. In order to do this inversion, in this work, we use Bayesian inference, which is simply a framework that combines prior knowledge of my parameters, again, the magnetic field and the orientation, with a likelihood function. The likelihood function compares some experimental measured signal with a prediction that I have computed. One advantage of our method is that since it's solely based on this geometrical condition of the magnetic field, the likelihood is computed very efficiently, and it reduces the computational cost. Because, as I said, I can simulate the signal of the PL signal really efficiently. I tested this experimentally with this setup in which I have 3 Helmholtz coils around my sample. The sample is illuminated with a green laser, and then I collect the photoluminescence, the red photoluminescence, with a photodiode. In this setup, I'm using 3 Helmholtz coils to generate magnetic fields in the 3 directions, also to generate the unknown magnetic fields that I want to determine. But in a real scenario, I would only need some objective with a rotating piece on top of it to which I glue the diamond sample. With that, I have the illumination part. And then by using a single coil to generate a magnetic field in one direction, and by rotating my diamond, I could measure the magnetic field generated by some sample that was sitting on top of the diamond. So the first experiment that we performed was to just calibrate the crystal orientation. So what we did was to apply a known magnetic field of 1 millitesla along the x-axis, and then by applying an extra magnetic field along the z-axis, by sweeping this magnetic field along the z-axis, and by rotating the sample, I obtain a experimental signal that looks like this one. Here, each darker line corresponds to a drop in the photoluminescence. This photoluminescence map, I can invert it using Bayesian inference. And what I obtain is probability distributions for the most likely orientations. Here, for instance, what I obtain is 2 tetrahedra. Each tetrahedra corresponds to one possible orientation of the crystal. In the crystal lattice, all the NV centers, the 4 orientations are oriented in a tetrahedra. So I have 2 tetrahedra, but they are both related by inversion. In fact, I cannot really distinguish between the one crystal and the inverted crystal. This is one limitation, but this happens in any magnetometry protocol. Just for reference, this orientation gives this simulated signal, which, as you can see, matches pretty well the experimental one. Now that the orientation is well calibrated, I apply the same procedure to determine a magnetic field. We introduced some unknown magnetic field, and we did the same. We applied a bias field along the z-axis and rotated the sample, now obtaining some map that looks like this. And now applying the procedure, I obtain probability distributions for the magnetic field parameters. Again, just for reference, this is the signal that I can compute for the estimated parameters. And as you can see, it matches the experiment. So with that, I demonstrated an alternative procedure that does not use microwaves or require alignment of the crystal, which is able to reconstruct some vectorial magnetic field. Right now, the limitation of our current setup, our setup is currently limited mainly by systematic errors. For example, this is a trace of the previous map, just one trace, one horizontal trace. And I'm comparing the experimental with the simulation. And as you can see, the dips, or the amplitude of the dips, don't always match. And this is because some specific experimental limitation that we had. Also, we see, for example, some tail around the right of the spectrum. And this is because some interaction of the NVs with carbon-13 nuclei in the lattice. But this kind of errors could be eliminated in an optimized device. Just as we expected, the uncertainty of the inferred parameters decreases as the square root of the number of traces. But what is most interesting here is that with a single trace, we are already able to extract the magnetic field. So this enables real-time operation in which both the measurement and the inference are continuously updated. So with this, I finished. This is the QR code in case you want to see the full paper. And if you have any question, I will be happy to answer them now.
So thank you, Hilario, for that nice presentation. And now, if someone has some questions, right there.
Thank you for the presentation. I am curious about why this method is more convenient specifically for metallic samples.
Because when you're using metallic samples and you are applying some microwaves, you might create some currents inside your sample. And this maybe maybe you don't want that because this could create heat in your sample, for instance. There could be some inconveniences that you don't want to happen.
Okay, thank you very much.
We have more time for questions, if it is another one. So thank you so much, Hilario. And now we can go with the next speaker, that is Lucas Ribeiro da Silva Santos from Universidade Federal de São Carlos. With his
Okay, thank you. It's working? Yes, sorry. Thank you very much for all the organizers for this conference. Good morning, everyone. My name is Lucas. I'm a PhD student in Brazil and a visiting student in CSIC Madrid. And one of my projects of my PhD is proposing a protocol of preparation of large Fock states in resonators with high probability. But Fock states is a well-defined number of excitations, number of photons, a pure quantum state, and it's very useful in quantum optics. And we have several of platforms that have already proposed how to, in this case, generating this kind of state. So we have in trapped ions, deterministic number states preparation. We have in cavity QED some protocols for using non-demolition measurements through preparing these states progressively. And now we have a huge path of development in circuit QED, trying to conciliate and preparing a large Fock state with a high probability, a high fidelity, and with a low circuit depth. So the challenge is when we increase the number of excitations, these Fox state is large is that we have a higher decoherence cost. And in deterministic protocols, this means that we'll need deeper control sequences. And we are looking for KND methods. This means that we have a robust method, robust approach, but it's probabilistic. So the probabilities of these photon numbers is suppressed, and we have a problem here. So our motivation for this protocol is to boost the success of probability of these Fox states using the platform of circuit QED. The idea of a protocol is basically in 3 steps. So we initially, for a coherent state, an initial coherent state, and we are interested to propose in a Fox state that is directly the mean photon numbers of this initial coherent state. For this, we are using 2 tools. Quantum phase estimation, very known algorithm for making a non-destructive field photon number of this coherent state using a dispersive interaction. And after that, we are using quantum amplitude amplification to amplify the probability of the desired state that you wanted to generate. How could we implement this physically? So it's a theoretical proposal and more fundamental system that we have a resonator, and in this resonator we have a coherent field, and in this coherent field is trapped in a single mode in this resonator, and these modes of this field, it's coupled with superconducting qubits. And this interaction, it's made by a dispersive interaction. So this means that I don't have an exchange of energy between the atomic state of these qubits and my field mode in my resonator. How could I construct this? We started by the very known model of quantum optics, that is the Jaynes-Combs model, and we apply some techniques like the Schiffer-Wolff small rotation, and we obtain an effective Hamiltonian, and we consider this effective Hamiltonian in the dispersive regime. And by this, I show you in the interaction frame this Hamiltonian that has 3 parameters that is very important. So this N is the A dagger A, related with my modes. I have the sigma Z, that is the atomic operator that will make the control in my protocol. And I have this dispersive shift. So if you see, all the qubits will have a specific dispersive shift, and all the qubits will have the same coupling. But I control this dispersive shift by the detunning, and the detunning is controlled by the atomic phase that I could change using an external driving magnetic field. So this is the idea of a squid, and how could we implement this in this physical model. So the idea is, how could I apply this physical model that is very general in the protocols that I told you? We use this using the quantum phase estimation, that is a quantum algorithm proposed in '95 by QTYR, and the general idea is, I wanted to estimate an eigenvalues of a unitary operator with a precision that would be directly dependent of the number of qubits of my quantum circuit. So the idea is now estimating the number. It's not so good, the quality of the image now, but the idea is to estimating the photon number of the coherent field in my quantum circuit using these qubits. So all the qubits are initializing in the ground state, and I pass this for a superposition using the Hadamard gates. And now my point is, my strategy basically will be to transforming this, applying the control rotations. So the control rotations that I'm showing here is the moment that we use in the dispersive interaction, so this H interaction. And the idea is, I could construct my unitary operator as I wanna. So the point is, I constructed my unitaries having the Fock basis as the egg states. In this way, I could capture the photon number of this coherent state that is this field state in the law of the circuit. And the point is, if I make some calibration conditions using the Hamiltonian, I could fix the interaction time, and I could vary the dispersive shift. And using this idea that is very feasible in superconducting systems, we could construct this unitary. I could now obtain phases related in each computational basis, Each phase will be related with a photon number, and I don't have more a photon number distribution, but I have a phase number distribution. And this will be important in the next step. So I just need to transform these exponentials, these phases, in terms of amplitudes for be measurable. And I use the inverse quantum Fourier transform to finalize the circuit. And now I have this phase distribution. So the next step is I need now to decompose my prepared state in what I wanted to increase the probabilities and the rest that I'm not interested in. And for this, I use quantum amplitude amplification. Basically, I will construct an arbitrary subspace of good states, that is what I wanted to amplify, and the bad states, that is what I don't want it to amplify. And the point is, I just needed to rotate in this prepared state by the KP using the Grover algorithm that is composed basically by two reflections. The first one is the phase oracle that will mark a phase in the states that I wanted to amplify, and the other one is the diffusion operator. And the point is, I need to apply this G, this Grover operator, in optimal numbers. So these are that depends of the initial probability of the states that I wanted to amplify. And as I said to you before, is the state related with the mean photon numbers of the current field. Of course, we could decompose this G operator of the protocol in many physical gates, but this is not the purpose of this presentation. My point is just to show for you two results that I have. So the first result is now the phase distributions. So we see now that it's not so different from the photon number distributions, but we have a mean for that. If you see the green bars, I have the Poissonian distribution. So I have this py, y. So y, it's an integer representing a phase, and is directly dependent with the photon number. And I don't have high probability for, in this case, the mean photon numbers of 3 photons, 15 photons, and 100 photons. So you can see that it's very scalable in this way. But the red bars show us, after I applying the amplification, so using the full protocol that I showed you before, I have these high probabilities, even for a large Fock state. So this is very difficult in some proposals. If you focus in a specific case, so using 5 qubits in my circuit, this is the probability of generating each state that I show you. So I'm increasing the number of excitations. And we see that just using KP, the probabilities are suppressed because it's the Poissonian distribution. But after applying the amplification, we see high probabilities. And of course, we see some oscillations in these probabilities. And this means this is because of the approximation that we make using this red solid curve here, because this is the number of times we apply the Grover algorithm, and we need to make an approximation for an integer number, and this could discompensate. I could rotate more than necessary my state in the arbitrary subspace. And just to finalizing, the idea is I could also see how this protocol behaves when I increase with a very high, large number of excitations, like this one in the Fock generator. So we see high probabilities for large Fock states, and we see that I don't have in this inset many numbers of times that I need to apply the Grover algorithm, because this R parameter is proportional to n 1/4. Of course, we could also analyze the system without using the amplification, just using quantum phase estimation. And how could this behave? So this eta parameter means how many times I needed to apply the amplifications, repeat, and obtain the results that I want. And we could see this in this result in this table. So for a small Fock state, I will need 3 qubits in my system. I will have a probability of 22%, and I will need to repeat the phase estimation 20 times, this eta parameter. But just making one phase estimation and using one amplification, I have a probability of 99%. And if we go to the state of 200, I will need to increase the number of qubits because I will need more distinguishable phases. I need to increase the precision of the circuit. so I need 18 qubits. I have a probability of 2%, so it's not an initial good probability, but after applying two Grover operators interactions, I obtain a probability of 99%. And if you make some estimations, so how many times I will need to apply all this protocol in my quantum algorithm, we have some, in our estimation, 20 to 25 microseconds. And the cavity lifetime to maintain this coherent field trapped in this resonator, it's around 0.5 to 2 milliseconds. So it's very feasible applying all this protocol in the cavity lifetime in the state of art that we have today, okay? So this is the presentation, guys. Thank you very much for listening and open to questions.
Thank you, Lucas. Now we have time for questions. So if anyone has, okay.
Okay, thanks a lot for the very nice presentation. So you discussed a little bit the limitations with respect to the cavity lifetime. I was wondering if you also thought about the fact, so here you are using up to 8 qubits a count. So these qubits, in principle, they need to be coupled uniformly to your waveguide.
Yes.
But to some extent, because you are using dispersive interactions, I guess you can also play with the driving frequencies and so on. So I was wondering if you thought about how robust this protocol will be to now not imperfections, let's say, in the cavity, but imperfections in the qubit, including the disorder and also the lifetimes of the qubits and so on.
Yes, this is a good question that Heferi made. I think for this work, this is not the purpose of leading with this, but some losses in the qubits like spontaneous decay, we are not considered in this way. But the point is, every simulation that we make here, it's we use, let me show. This is not so good, the quality, but for every simulation that we made in the quantum phase estimation, we are considered one simulation of the quantum trajectory using Monte Carlo. So this could be a way to simulating the decay of these qubits during this dispersive interaction. And we have, of course, the cavity lossy, but we need, I think, I don't know in the future we will explore this or not, but this is a good point, yes, to explore.
But your platform, the platform you are thinking about, is the one that you had right in the next slide, I think. So it's right. So it's superconducting or transmon or flux qubits.
Yes, the qubits could be a squid, and of course we could explore more imperfections in the squid. Yes, but as is theoretical proposal, we could also turn this around because we could control this this coupling as we wanna, and compensating some problems, some imperfections that we have as we wanted to define this very precise decoupling. So all the parameters is we could control them very well using quantum circuits.
Yeah, cool. Thanks.
Nothing.
Are there more questions?
Like that?
Yeah, my question is the Grover operator you have skipped very quickly. Yeah, I think your challenge is to implement the Grover operator in the circuit, but I can't catch the slide you presented us, the Grover operator.
Sure. Yes, I'm trying to apply the Grover.
The more times you implement the operator, and the more gates you have to.
Sure. Yes. This is the principal discussion because, as I said, this is a slide that have a very conceptual way in the paper, because this G is the Grover operator, and this G basically is composed of the two reflections that I told you. So I have the phase oracle that I'm calling as good, and I have this asp psi that is the diffusion operator. So your question, it's basically not how could I do this, because this is basically a phase oracle marking with a phase, a control Z in the states of the qubit states. But if we look for the diffusion operator in the Grover algorithm, it's a very, very high cost gate. In principle, because we need to, in this case of the diffusion operator that I have, basically is a reflection on the prepared state. So the idea is I apply the Grover operator in a specific state. I mark with a phase operator, but I need this original state again. So it's a reflection on the prepared state. This is the definition of the diffusion operator. For that, what this means, I will have to apply all the gates of the quantum phase estimation again. I need to uncompute this because this means these daggers, and compute again. So this asp psi, it's a high cost gate, and we need to take in account. But as I told you, it's a theoretical proposal. So our idea is not to measure the efficiency of the model, but to measure the quality of the probabilities that we obtain. So we could obtain high probabilities. This is a theoretical proposal, so I don't have so much trouble to simulating this numerically. This is what I made. I don't make an experiment with this. But this asp psi, it's a problem doing experimentally. As the Grover operator, it is, when we need to make many times.
Yeah, if you calculate the fidelity instead of the probability, you have to consider the successful probability if you have so much gates, and you also assume you have to recite or something like that. The probability may decrease very quickly, or something like that. I think it's a very challenging. Even you implement experimentally, something like this. Okay.
We could talk later, but yes. Yeah. Sorry for the time.
So thank you, Lucas. And now we go with the next speaker, Jaime García Oliván from Universidad del País Vasco, with his talk, Surprising Fast Dipolar Noise in Solid-State Spin Qubits.
Thank you for the introduction. So my name is Jaime. I'm a PhD student at the University of the Basque Country in the group of Jorge Casanova. And today I will be speaking about methods to suppress fast dipolar noise in solid-state spin qubits. So spin qubit coherence is a fundamental resource for the realization of quantum technologies. Now, in solid-state systems, the main source of the coherence is the magnetoactive environment in the lattice, which is typically very difficult to suppress. So typical methods to suppress noise in spin qubits are echo-based techniques, which are very efficient in suppressing slow noise, but however, they remain sensitive to the fast noise that may arise from, for instance, strong interactions within a spin path. This work that I'm going to present here is one of our latest works in our group. And for this, we have developed a numerical framework that allows us to study the coherence of a central spin due to a surrounding spin path. And we have used this method to propose a novel protocol that is called hybrid LG, which combines resonant and off-resonant driving tones to efficiently suppress fast noise in these solid-state systems. So we can find spin qubits in many different systems in solid state. One of the most prominent examples is the nitrogen vacancy center in Diamond, which has already been introduced, so I'll try to be brief. So the MV center is a substitutional nitrogen defect that is coupled to an adjacent vacancy, here in white, where an accumulation of electrons gives rise to a spin-1 system, which can be initialized into the zero state via laser illumination and can be controlled through microwave radiation resonant with one of the two excited states. So to protect the coherence of these MV centers or any other spin qubit, the easiest method is to use a spin echo sequence, in which we prepare our qubit in a coherent state, and then we allow evolution under some magnetic field so that it accumulates some phase. Then a pi pulse here just mirrors the state of the qubit along the pulse axis, and such that a final evolution just cancels the phase that was accumulated during the first evolution period. And in this way, at the end of the sequence, the slow noise is effectively suppressed. However, when we have fast noise, this is noise that changes during the duration of this sequence, these techniques are not able to suppress this noise. So we need to find alternative methods. And where does this noise arise from? So typically, we have central spin here in black, which is surrounded by a spin bath. And these bath spins interact dipolarly, such that they generate an effective noise field that is coupled to the central spin. And the noise dynamics that these interactions generate are strongly dependent on the interaction coupling between the bath spins, which, for instance, for an electron bath, they are pretty strong, which give rise to fast noise. And to address this noise, what we can do is just tackle the origin of the noise, which is directly the spin bath. So we add a continuous bath driving of some strength omega and a detuning delta. Now, the standard approach here is to use a resonant driving. And this means that the tuning delta is 0, and when we apply this driving, we are generating Rabi oscillations of the bath spins, which decouple the bath from the central spin as long as the Rabi strength of the driving is larger than the coupling between the bath spins and the central spin. But we can instead allow some detuning. And it happens that when this detuning matches a particular condition, that is that delta is plus or minus the Rabi strength divided by the square root of 2, which is called the LG condition, Lie-Goldberg condition, then it happens that the interactions between the bath spins are cancelled. And this means that the time dependence of the noise that is sensed by the central spin disappears. And then a simple spin echo sequence is allowed to just fully suppress this noise. Okay. However, the question now is this better than the standard resonant approach? And the answer is that sometimes. And in general, in solid-state systems, it won't. So now we need to find maybe some alternative protocol that uses this Lie-Goldberg condition and performs better than the standard resonant approach. And why doesn't this method work? So when we have, let's go back to Diamond. So in Diamond, the MV center, the main source of the coherence of the MV center is a bath of P1 centers, which are substitutional nitrogen defects coupled to an electron, such that there is a hyperfine interaction between the nitrogen spin and the electron spin. And what this does is create different energy states of the bath, depending on the orientation of the P1 center in the lattice and the nuclear spin state. And we can probe the bath with a DIR sequence, and with this we find out that there are, in this case, 4 different energy levels of the P1 bath with different populations. And when we have 2 P1 centers that are in different energy states, the interaction between them is suppressed. But when we apply this LG driving, although we cancel the interactions of P1 centers that are in the same energy state, we are creating interactions between the P1 centers that are in different energy states. So at the end, we get no practical coherence improvement. So what we propose is, instead of driving the whole bath with some LG driving, we propose driving part of the bath with a resonant driving and part of the bath with an LG driving. And what this does is the part that is driven with resonant driving is preventing this revival of interactions, while the LG driving is providing a better coherence improvement. So With this numerical framework that we developed, we studied the coherence time of an ensemble of MV centers due to the surrounding P1 path. So here we're plotting the coherence time of the ensemble as a function of the concentration of the P1 path. In this case, for the case where we are not driving the path. And we are going to focus mostly on this regime, because this is the regime that most diamond samples nowadays are utilizing, and as well as the regime that our experimental collaborators use. So this is the one that is of interest to us. So then we can apply a resonant driving, a two-tone resonant driving that is targeting the two most populated energy states of the path. Why two tones? Because this uses less power, and we are focusing on scenarios that do not require really high power, because this could create some heating effects that affect our system, and we want to prevent that. So we focus on low power scenarios. And we see that even with when we are not driving the whole path, we're still getting a 3 times improvement in the coherence time just by using this resonant driving. And what we can do is just take one of these tones and detune it a little bit to match the LG condition. And just by doing that, we found out that we get an even further coherence improvement. We get a twofold improvement with respect to the standard resonant case. And how good is this improvement? Well, it turns out that if we drive the whole path resonantly, we get a similar coherence time of the ensemble. But this requires a much higher power consumption, and that's what we are trying to avoid. So with this protocol that we are proposing, we are getting it's more efficient than the standard resonant approach. We get better coherence time, and we are consuming less power. So yeah. This is the work that we've been carrying out, and we are now trying to demonstrate it experimentally. But for now, the simulation results are looking pretty good. And with this, thank you for your attention. You can read the full article on arXiv, and then you can also visit our GitHub page to look up the code. I'll be happy to take questions now.
So thank you, Jaime. And now if someone has a question. Okay, if not, I have one. I was regarding what do you mean when you talk about your methods? You need less energy. Why you need less energy to the whole process?
So we mean less power when,
for example, yeah.
Yeah, because so each tone that you apply, each driving tone you apply requires more power. You're increasing the number of tones, so you need to put more power into the system so that you can address the whole path. And with this, we are cutting a lot the power consumption. We are cutting it 4 times.
4 times, okay.
And we are getting almost the same coherence improvement.
Okay, thank you. So, thank you again, Jaime. Now the next speaker is Carlos Sagaseta from Universidad Carlos III in Madrid.
Thanks for the introduction. Good morning, and thanks to the organizers for this opportunity to talk about my work titled Fidelity Bounds for Speed-Dependent Kicks with Pulse Lasers, which was recently published in the arXiv. And this means how good we can perform a speed-dependent kick operation on a trapped ion, and we will see what it consists of. But before, I will give a brief introduction to trapped ions and the types of gates that there are, highlighting why speed-dependent kicks become important in the context of fast gates. So, atoms with a net charge can be trapped with electromagnetic fields in devices like this. So there we have a trapped ion. And we typically use isotopes in the group 2 of the periodic table, since when ionized, they have a valence electron whose state we can manipulate. So in the context of quantum computing, trapped ions exhibit extremely long coherence times. They also hold the record fidelities for all these operations. However, 2-qubit gates still remain as a limiting factor when it comes to applying them in a long string of ions in a scalable device. So regarding gates, in terms of speed, we find these two types of gates, where adiabatic gates, they're based on addressing spin-motion coupling sidebands in times longer than the motional period of the ion. So when it comes to longer strings of ions, there are more motional modes, so the spectrum becomes crowded, and it becomes increasingly difficult to address the sidebands without, unwanted coupling. So in order to overcome this quantum charge coupled device was proposed, where ions are moved between interaction zones and, memory zones and interaction regions, where these adiabatic gates are performed in small ion registers. However, it still remains this high fidelity versus speed bottleneck, which comes from the transport of the ions and the subsequent cooling before the gates. So that is where fast gates appears to overcoming this high fidelity versus speed trade-off. So instead of addressing single or individual modes of motion, geometric gates are, the principle of operation is impulsively exciting the ions, and the working principle is closing, with free evolution times in between. So the working principle is closing trajectories in phase space so that, a geometric phase is accumulated, which is independent of the initial state and temperature. So here's where spin-dependent kicks come. Each one of the kicks, impulsive kicks in the geometric fast gate scheme constitutes a spin-dependent kick, which mathematically, and as the name says, it consists of on a spin flip and a momentum kick whose sign depends on the spin state. So we will, by targeting this operator, we will tune the experimental parameters using the infidelity as a figure of merit. So how can we actually create a spin-dependent kick? So in the model, we have a trapped ion in an approximate harmonic potential with frequency omega t. So we also have the qubit levels, which in our case, they are hyperfine gigahertz splitting. And each interaction consists of counterpropagating laser beams with this linear perpendicular polarization, so that this term in the Hamiltonian appears that allows for the spin motion coupling. So in our case, we will take the laser beams to be trains of picosecond lasers proposed by Ms. Rai et al. So the motivation for improving the fidelity of these SDKs, spin-dependent kicks, is that the conditions necessary to generate the spin-dependent kick with this pulse train were derived taking 3 approximations. So the first one was assuming an infinite number of pulses, which is unrealistic experimentally. Also, it was assumed that the pulses are instantaneous compared to the qubit evolution. And last, assume that the ion is not moving because the dynamics of the gate is really fast. So in order to get more realistic fidelity limits and improved operation, we sequentially remove each one of the approximations. So first we will consider pulse trains with a few number of pulses for faster gates. We will consider the true temporal shape of the pulses as a Gaussian envelope. And in these two cases, since we're still considering that the ion is not moving, we will make a semi-classical description, meaning we'll take x position as a constant of motion. And last, we will simulate the complete model allowing the ion to move. and see its effect. So with that, I go on with the results. So starting with an initial state of a spin down and an motional ground state, we see this parameter space which depends on these two angles that are related by the repetition time between the pulses, and this delta is the frequency difference between the Raman beams. So here we have that those two equations are the optimal conditions for the creation of a spin-dependent kick under the infinite pulse number approximation. And so if we take a deeper close look at these cuts, we see that the infinite pulse number condition, better said, the line where the optimal points appear in the few pulse case is better than the infinite pulse number condition. And also, second result is that as the number of pulses increases, the local minima, where there appear more local minima, and they exhibit better fidelity. So that is also in correspondence with this infinite pulse number limit. So we also study taking these optimized points at each number of pulses. We represent those, the optimal infidelity versus the number of pulses, and see this power law scaling with the pulse number. So we study the dependence with the lambda key parameter and with the temperature. So in both cases, we can explain this behavior with this figure. So remember, we are simulating the dynamics at every position. So here in the right axis we have position, and in the y we have a figure of merit, which is related to the fidelity. So as the width of the motional wave packing increases, we see that the ion sees contributions of the operation where it is not perfectly performed. So that is why the fidelity deteriorates with increasing lambda key parameter and temperature. So then we continue to removing the next approximation. So we simulate the true temporal shape of the pulses. And in this case, the qubit-free evolution and the pulse do not commute, so they constitute a rotation about an axis different from the instantaneous pulse approximation. So we see that as the pulse width increases, the infidelity deteriorates very much. So, for example, for a number of 10 number of pulses, we see the infidelity gets an order of magnitude worse, and to an order of magnitude worse for 20 picosecond pulses. So we also found an analytic bound, which although is pessimistic, it predicts this saturation of the infidelity. So we simulated this ion species with that hyperfine frequency, so we can relate where this instantaneous pulse approximation works, which for this case, it works for 1 picosecond pulses. And last, we simulate the complete model. So in this case, we will compare a simulation where here to the right, we have the path where we don't have ion motion. So we have the ion which is kicked n times until reaching a final, the state we target. And in the left, we have the case where the ion is moving. So we see that it deviates from the ideal state, and this is the error we will quantify. So looking at this figure, for two different pulse widths, we see that in both cases, the infidelity with and without motion are pretty much alike. So we see in the figure at the bottom that the error is of the order of 10 to the minus 5, and it adjusts pretty well to this theoretical bound we estimated. Notice that the pluses and the crosses are the infidelity calculated using the semi-classical model, where the position is treated as a parameter. And with this, I conclude. So we extended the theory by considering finite trains of pulses to optimize SDK infidelity. We found that it scales as a power law with the number of pulses, and that it deteriorates with increasing width of the ion width packet. Also, the main source of infidelity in our case was the pulse duration. So it works very well with pulses of 1 to 5 picoseconds. And the source of infidelity is much larger than the error due to ion motion for nanosecond long SDKs. So the outlook of this work as an extension of this kind of simplified scheme where we consider equally spaced and equal amplitude pulses, we could extend the optimization space to allow for amplitude modulation and unequal arrival times. And by taking all these results, we can gather this together to achieve even better fidelities. And also we can compare this pulse scheme that we restricted to a continuous wave excitation, also amplitude modulated, and see really what are the fundamental limits of the infidelity. So with this, I thank you for your attention, and this work was done in collaboration with IonQ. You can have a look at the preprint if you want.
Thank you, Carlos. And now we have some time for questions.
I was wondering, how do you define the acceleration? Because you compare the adiabatic gate with the fast gate. Yeah, I mean, you have to fix some factor, like you use the same energy to drive these two gates, and the fast gates, its infidelity drops more quickly, or something like this.
So you mean where do I differentiate between adiabatic and fast gates? Or?
Yeah, you compare the two gates, right? And the fast gate is more faster, but how do you define this faster gates?
So this time scale. Well, their principle of operation is completely different. So in the fast gate scheme that I showed with the simulation where the principle of operation is closing a phase space trajectory. So depending on the number of ions, you need to close each mode's phase space trajectory. And where in the adiabatic gate case, you achieve spin motion coupling just by addressing one mode of motion. So the principle of operation is different, and so both time scales are very well separated. And so the adiabatic gates they start to fail when, of course, when they get faster, when you try to get them faster. But the fast gates, you can get them faster than the trap period of the ion in the trap. But those time scales are very well separated. I'm not comparing where they overlap, but I would say fast gates are in the few microsecond to sub-microsecond timescales, while adiabatic ones are hundreds to thousands of microseconds.
Okay, I think you put 2+ to the fast gates. I mean, you need more energy to drive this gate.
In terms of energy, so for every spin-dependent kick, you're driving so for a spin flip, you're driving a pi pulse, and you need many spin-dependent kicks for the fast gate scheme. So that would depend on how many spin-dependent kicks, the energy, how many you need. But in terms of energy, I'm not sure.
Yeah, if it's a Hamiltonian, I make it 10 times Hamiltonian. It's more faster, actually. But what do you do? If you fix the same energy and the fast gates, it's faster. I think it's truly faster. But the energy doesn't fix. I just put more energy to the gate, and I see it faster. I can buy it. That's my point.
Maybe we can discuss later, but...
Okay.
Yeah, sorry.
So thank you so much, Carlos. And now... we go with the next speaker, that is another Carlos, Carlos Martín Fernández, from Instituto de Ciencias Materiales de Madrid.
Hello. Yes, it's working. Hello, everyone. As said, I'm another Carlos, but with a different topic. Today, we're going to talk a bit about flocked geometry phases of a strongly-driven qubit, and in particular, we will present a protocol in order to measure them. I just want to remark that this work has been done in collaboration with both Gloria Partero and Sigmund Kohler. And first, let's introduce some concepts in order to properly understand the physical relevance and how the protocol can be implemented. First, let's talk about geometric phases in quantum systems. For a generic Hamiltonian, we know that if we propagate through a closed path, we will acquire a phase. And for a long time, this phase was thought to be exclusively dynamical. So we can see on the screen, depending only on time and energy during imprint of the Hamiltonian evolution. However, in 1984, Michael Berry discovered that if we adiabatically vary the parameters during a cyclic evolution, there will be another contribution, which is purely geometric. And by geometric, we mean that it only depends on the path rate on the projected space, not the rate, the duration. And this was initially studied for adiabatic systems, but 3 years later, Aharonov and Anandan generalized this concept for any cyclic evolution, so that we could study non-adiabatic situations. Our protocol is heavily based on the experiment that was performed by Leak et al., in which they were able to observe the very phase of a solid-state qubit by slowly steering the effective field of the qubit and reading out the solid angle phase using a spin echo sequence that allowed the cancellation of the dynamical phase. We remarked that the experimental requirements for our protocol are exactly the same. Indeed, if they still have the circuit QD chip used for their experiment, they could test our experiment and try to see the results. We want to remark also the main difference, because we are not recreating the same protocol. We are not basing the dynamical phase cancellation on spatial chirality properties, as they did in their experiment under theoretical study, but we use spatiotemporal chirality, so we will make use of flocked theory in order to address this problem. Besides, we have already mentioned that we want to measure non-adiabatic phases and Andan phases, so that our protocol is able to go beyond these very phases in order to measure the non-adiabatic ones. As I have already mentioned floquet, let's change our aim to the study of periodic systems. The floquet theorem tells us that for a Hamiltonian which is time periodic, the wave function admits a decomposition in a phase term, which is characterized by Q alpha, which are the quasi-energies, and the floquet modes, U alpha. These floquet modes are time periodic. As they are time periodic objects, they admit a Fourier expansion, something which is really useful in order to obtain high precision numerics. Using all these properties, we can derive an expression for the Anandan phase of a floquet state, which we call floquet Anandan phase. In particular, the floquet Anandan phase will coincide with the Anandan phase over a period of a Schrödinger state. So we can name them both Anandan floquet phase or Anandan phase, in case I use both names during this small talk. Lastly, as I have already mentioned in the title, we are studying qubits. Therefore, we need a model to study. And this is the Hamiltonian for a two-level system of a strongly driven qubit, in which we have the channel splitting, characterizing, and also the external driving with an amplitude A, frequency omega, and the drive phase theta, which will be really important. On the right, we see all the mentions magnitudes of this floquet theory. We have the Anandan phase, the quasi-energy, and the mean energy. And we want to remark the relation that they all keep together
which tell us how the mean energy splits into dynamical and geometrical. Now I want to exploit a feature of the floquet theory, which is one of the cornerstones of our protocol, and basically is that time shift equals drive phase shift. This is given by the fact that if we shift time by a quantity tau, we are obtaining the same result as if we were shifting the driving phase theta quantity omega tau. We can compare the overlap of the two shifted Schrödinger or the floquet states, and we will obtain that they are the same, and they will only differ in a global phase. And we know that a global phase is a gauge degree of freedom that can be gauged away. This way, what we can do is that we can slowly variate the phase theta in a loop from 0 to 2 pi in order to measure the non-adiabatic floquet and random phase over a period. This way, they both will trace the same path in the projective space, so we can establish an equivalent between both phases in order to measure a non-adiabatic object by the adiabatic variation of a parameter of the Schrödinger qubit. Now we are in terms to explain the protocol, which is quite simple and quite analogous to the leak experiment. This protocol is based on 2 loops and 2 pi pools. Let's go step by step. First, we have 2 loops performed in opposite direction, and we know that the geometrical phase depends on our path, so that if we perform opposite direction, we will obtain opposite geometric phase. But someone would say, okay, this implies a cancellation of the geometric phase, and you said that you want the opposite, to cancel dynamical phase. And that's when the spatiotemporal chirality antisymmetry of our floquet operator, our floquet Hamiltonian, enters in action. If we transform our states and our Hamiltonian with a composite transformation with the pi pools, which is sigma y, and the time reversal operator, what we obtain is the equivalent of propagating our state with minus the Hamiltonian. And propagating with minus the Hamiltonian implies that the total phase of the state would be the opposite. So now, instead of having a suppression of the geometrical phase, we'll have a suppression of the dynamical phase and an addition of the geometric one, so that the total phase acquired on the 2 loops will be 4 times the floquet Berry phase, as we obtain the relative phase in each of the loops. Besides, we just want to comment that in order to be able to apply this particular transformation, we need a point in theta in which we have time reversal symmetry, and this is given in any point in which theta equals a half integer number of time of the period, and 2 pi is a perfect candidate. Lastly, on the right, I want to show some of the results, because we can parameterize, in order to measure this adiabaticity, the theta parameter as our drive frequency omega divided by n loop. This way, n loops will control how adiabatic our result is. And in particular, we see that we obtain adiabaticity with a really low value of n loop. However, things are not as beautiful as we want, but they can be. And there are some physical mechanisms that can break adiabaticity. This occurs whenever the gap of the quasi-energies becomes 0. And there are 2 physical mechanisms that imply this. First is the coherent destruction of tunneling, which is one of the quantum effects most studied. And we know that if we sweep the amplitude, we will reach points in which the quasi-energy gap closes, and this occurs for the zeros of the Bessel function. And we cannot resolve the floquet and random phase, so that we can try to look our way to engineering, and this is obtained by adding a static detuning, which is perfect, as it still preserves the spatiotemporal chirality and opens the gap flow. However, adding detuning to our model implies that there will be multiphoton resonance. This multiphoton resonance occurs when the unfolded quasi-energy gap equals an integer of the driving frequency, so that the folded quasi-energy becomes 0. On the right, we can see a map with the 2 phenomena on the same time, so we need to look for a path that avoids them. Now, I will introduce briefly how the protocol is implemented experimentally. We can see on the right all the steps, and this is a briefly expansion of what's already mentioned. In order to be able to measure this phase, we need to prepare the state, and we prepare a coherent superposition at zero amplitude. The zero amplitude condition is given so that the flocked eigenstates coincide with the instantaneous eigenstate of sigma z, so that we can later perform a classical tomography in order to measure the relative phase. Then we will ramp the amplitude until the desired value. This is performed linearly in a fixed value of theta, so no geometric phase is accumulated during this process. And the adiabaticity condition for this ramp is really, really loose, so there's no need to get into detail, as the previous condition is straighter. Then we perform the protocol, as is already mentioned, and we ramp down again the amplitude, so that we reach now a state with no amplitude in which we can perform the standard tomography. This will let us measure both sigma x and sigma y, and the relative angle will give us the Floquet-Anandan phase, which is 4 times the Floquet-Berry phase obtained by varying theta. These are some numerical results that illustrate, because we can see that both pictures A and B are pretty similar, but still we can see there's some regions of discrepancy, which are the 2 multiphoton resonance of m equal 1, left and right, and in the center we have the first 0 of the coherent structure of tunneling. And experimentally, we need to look for paths that avoid this region, so we cannot stay in the neighborhood, but it's something that is pretty achievable. And with this, I want to conclude and give my main remarks about this project. First, we want to remark the possibility of studying a non-adiabatic magnitude by varying and manipulating a really controllable adiabatic one, which is something really interesting, as it's really controllable in experiment and allows the measurement of a magnitude that one initially could not go. Secondly, we want to mention that with all the physical principle explained, we're able to construct a protocol based on experiments, so that is feasible, and we can establish a way to measure this Floquet-Anandan phase of a driven qubit, a strongly driven qubit. Lastly, we just mentioned the experimental requirements are the same, and in case anybody wants to know more about the technical details, because we have used many numerics and analytic expressions, the proofs and results will be published really soon in CONMAT with Carlos Martin et al. And in case you want to make any question, I'm happy to answer, and thank you very much for your attention.
So now, if someone has some questions, it's time.
Be careful.
Thanks a lot for the very nice talk. So I have a I think it's very stupid question. So at some point you wrote a formula for the Floquet-Anandan phase.
Yes.
And I saw this was expanded in some the Floquet modes, basically.
Yes.
Why this is so you have a bracket there? Are these functions not normalized? Why do you keep them in this formula? Or is it because are there just regular? Aren't just an orthonormal basis?
Yes, it's the Floquet Fourier basis that we call it.
Yeah.
So basically, normally, how you can address Floquet problems is transforming into a infinite value Fourier expansion, so that we play with the Fourier coefficients, and the bracket is notation. So these are normalized by direct diagonalization.
Okay, and just a follow-up question. So this protocol that you developed here, it seems to you were inspired by the experiments, the original experiments doing on qubits, but in principle, it seems like you should be able to extend it also to other systems, like a bosonic system with interactions, or a multi-level system. I don't see anything that prevents you from doing that. Or am I wrong with this?
No, you're totally right. Indeed, I've mainly mentioned this experiment in order to show that there's a current platform that can implement it. But yes, we can try to implement this because it's based merely on physical principles, not on approximation. We can try to implement this to different systems, as you mentioned, bosonics or quantum dots. or as in this case, superconducted qubits. So yeah, it could be implemented in different platforms.
I see. But so my point is that in general, you don't rely on the geometry of the Bloch sphere for this.
No.
Do you? Okay.
Normally, that's only used for adiabatic studies, and even though we are doing an adiabatic manipulation, the object that we measure is not adiabatic, so we don't rely on Bloch sphere characteristics.
Okay, cool. Thanks.
Thank you very much.
So thank you, Carlos. And now we go with the last talk. That is from Benji Tirado from CSIC, and it's titled Utility Scale Dynamic Circuits to Address Collective Dissipative Effects of Interacting Qubit Chains.
Congrats, baby. Okay. So, hi everyone. I'm a PhD student from the Basque Country. And today I will talk to you about my work, which we actually uploaded to the archive. You have there the QR code. And it's going to stay there in the top right corner for all the presentation, just in case you say, oh my God, this is exciting, let me check. Then you have all the details to everything in the archive. So yeah, so the main purpose of my work is to try to model dissipation using quantum computers. And just to give you a little bit of background on this, so dissipation, of course, is essential for quantum technologies. On the one hand, for example, say you want to design some qubits, you know that because of the qubits are interacting with the environment and the environment suppresses entanglement, this can really limit the quality of your qubits, for example. Also, if you want to study some simulations in physical systems and their interaction with environments is essential because they have many losses or dissipation going on, of course, you will have to take this into account when modeling and simulating your system. So, now, more concrete on the simulation of open quantum system dynamics using quantum computing, there have been many algorithms proposed in the past. As I just highlighted here just 3 of them. The main issue I would say they all share in common is that they scale really poorly with the system size. So if you want to simulate many battle systems, this will result in very deep circuits. And in quantum computing, the deeper your circuit is, so the more 2-qubit gates, most importantly, that it has, the noisier the result you will get will be, so the worse computation overall, right? So we want to obtain these shallow circuits. Now, my work relies on using this just simple system. You have many interacting qubits, and they're not only interacting with the nearest neighbors, they also have some self-emission process going on and some cross-dissipation also with the nearest neighbor. And how can we model this dynamics using a quantum circuit? So like the scheme in general is something like this. You map every qubit to a qubit in your device, and then you make use of some ancilles or extra qubits that will kind of represent the environment and help you model this dissipative process. So basically, I'm not going to go too much into detail, but we use this really simple circuit that uses just 1 qubit for your physical qubit and 1 ancilla qubit for the dissipation. And we use the ideas from the circuit to construct a more, let's say, involved circuit that not only models the single emission of each one of the qubits, but also this cross-dissipation. And now you can take this unit for the 2 qubits and kind of do first this 2-qubit circuit to the even qubit pairs. So here it would be first you do 0, 1, and in parallel 2 and 3, and that's 1 layer. And then you do the odd pairs. You would do here just 1 and 2. So which this construction means is that the more qubits we add to the system, we're not adding more depth to our circuit because they will lie on each one of the 2 layers that we have. So this construction on paper is independent on system size. I mean the depth of the circuit. So this is really good for running into actual hardware. And if we do just a classical simulation of the circuit, we get really good match with the exact classical solution up to some approximation error. And so here you would say, okay, you already have a circuit, you can run how many qubits you want, and you're not going to get really deep circuits. You have already finished here like your work. But the main idea of my work also is to run the circuits on the actual quantum computers that we have right now. So when transitioning from that classical simulation of the circuit to an actual simulation on the device, we have to realize what are the limitations of our circuits. So first of all, the main issue is that my circuits are already quite deep. Now, you might say, okay, this doesn't look that bad. You don't have that many gates. It looks quite simple. But this is not the actual circuit we're running on the machine. This is the actual circuit that we're running. So this is a transpilation process, which basically means translating the circuit you just came up with, the gates you came up with, into a language that the actual quantum device understands. So this involves several steps, let's say. So first, we have to map those virtual qubits to actual physical qubits on our device. Then we also have to translate our custom gates into basis gates that the device understands. And most importantly, whenever we want to make some qubits that are not right next to each other interact, maybe let's say you want this qubit talk to this qubit, you have to swap them around the lattice so that they can interact. And this, of course, inserts more gates, so more depth to your circuit. Now, this, again, with our particular circuit, we don't have a really good connectivity for the topology on the IBM quantum computers. And this also results that when we actually translate these circuits, we lose that size-independent scaling of the circuit, and we get really unstable, unpredictable scaling, so really deep circuits, bad results again. So how can we solve this or try to improve this? So this is the original construction, and we realized that we can reduce a lot the depth by moving to dynamic circuits. So dynamic circuits that you see here, it has some measurements that are performed mid-circuit execution. You store the results, and depending on whether you got a 0 or a 1, you would apply one block of operations or the other. So with this construction, we already have a much lower depth, you see, but still quite unstable. How we improve this is really, again, you have all the details in the beautiful paper in the archive, but just really adapting. The idea is that the more you adapt the circuit to the topology, of course, the better the scaling would be and the more promising the results will be. So now that we have this final version for hardware, we run this, we measure some observable, and as you see, we did this for, I believe, 10 system qubits with the Enceladus 15. And the results we get from the machine are not quite bad, they're quite good, but we could do better. And how do you do better? Usually in quantum computing is using error mitigation. So this is the particular technique. In the paper, we discussed also Z&E, but here, this was the one that performed the best for our circuits. And you basically have the circuit, you want to mitigate the results, and you generate a set of training circuits that are like similar to the problem circuit, but they are fully Clifford, in the sense that you can run them efficiently on a classical computer. So you take this set, you run that circuit, those circuits, on your classical computer and on your actual quantum device, and you would get a plot. You could plot the ideal result of that, the expectation value of those circuits in your classical computer, and the ones you actually got from the machine. Then you can use that to train a machine learning model. Here's just simple linear regression model that will correct your original observable in your problem circuit. So we use this technique, and as you see here, we managed to really improve the raw results from the machine. So now that we got a technique that works, we said, okay, let's go to bigger qubits, bigger chains. This is the biggest we did, which involves a total of 129 total qubits in the IBM Basque Country quantum computer. And as you see, we got that chain going on. And at this point, you say, okay, you got the result from the machine, and you got the corrected, but what is the actual solution? Because 129 is well beyond exact brute force calculations. So for this, we also developed a custom hybrid tensor network and Monte Carlo technique to kind of validate these results. And again, you have more, you can ask me or you can check the details. And if we go back to this and we plot this solution, we get really good match from this large-scale experiment. And yes, so just to sum everything up, I have told you how you can adapt your circuits to actually match the topology of the machine and get the best results that you could get. Also, how error mitigation can really help you get that push on the quality of your results. This really cool technique that I didn't get into detail, and this simulation on 100+ system qubits. So the acknowledgement, and again, huge ass QR code if you want to check out the paper, and thank you so much.
So thank you, Benji. And now we have time for questions. Yeah. Okay. So someone can pass to her the cube.
Hello. Okay. Hi. Thank you very much for your talk and for the beautiful QR code.
Oh my God.
I have a question. How cost efficient is this machine training part of your protocol? Because I guess that at some point, depending on the circuit you want to implement in the quantum computer, training this model has come with a higher cost. No? At some point, you cannot simulate these quantum circuits in your classical computer. No? So my question is, until what point can you do this? So it's for small quantum circuits, as big as we want? How have you worked with this?
Okay, so the thing is, your circuits, if you construct them fully Clifford circuits, they are always going to be classically efficient. On 100+ qubits, you can run them actually on your laptop, and they run quite well. The actual cost that you have here, I would say, comes from the quantum execution. Because apart from your problem circuit, you have to run, let's say, like 100 extra circuits just to train the model to correct your observable. So you have to run per time step 100 more circuits than the one you're running. And maybe you have a more complicated circuit with more gates or more measurements. It's something that requires going even to 200, 300 training circuits. I would say that's a really, yeah, the quantum cost is quite high, yeah.
Okay. Thank you.
Thank you.
So, well, we are in time, so thank you, Benji. And, well, with that talk, we finished the contributed talks in the Monday morning. And now I think that is time for lunch. So thank you so much.
Let's go.
Okay. We will be back at like 2:30. We have been informed that there are, in all these streets near the center, there are a lot of restaurants, a lot of options to eat lunch if you are interested. And yeah, see you in the afternoon. Thank you.